Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step one inside as we jump into section 4.2 in the Big Ideas Math Integrated Math 3 textbook. This is on properties of radicals and rational exponents. So these are ones you probably have seen in some of IM1 and IM2. I don't know, we got to revisit some of them as well, and we'll see what we have to do to expand on them. Now, this is the kind of section where I struggle with. I don't struggle with on a way of being able to answer the questions. It's that there's more than one way to answer a question, and I need to generally go through them slowly when teaching them, you know, as far as how I do them. So sometimes I'll say, here's a way you can do it, here's a way you can do it, whatever. I'll try and stick myself into just one way only because we have a total of 82 problems. Or it might even be more. I have to make sure it was even 82, but it's 80 something. I know as a for sure. So that's what I have written as 82. Let me check this as I keep talking. So anyway, just understand that there is more than one way to do these problems. It's all about being creative in the process, and sometimes people have a better visual. It's 82. Sometimes people have a better visual version of what they want to do versus others, and I'll give you the reasons why I do what I do. And if you get really good at it, then you can go pretty fast and pretty efficiently at it. Without further ado, guys, we're going to go ahead and get started. We're going to find the simplest form of a radical, and that's any radical, not just simplifying square roots anymore. Cube roots, fourth roots, sixth roots, whatever they are, as long as you know perfect powers within there. We're going to talk about conjugates tomorrow. We've talked about complex conjugates, irrational conjugates, but now we're doing those, at least irrational ones, in the form of rationalizing denominators, which is actually what you see here as a previous term. And like radicals, which is kind of like terms. When you combine like terms, you can also combine like radicals through addition and subtraction. So we're going to go ahead and get started. You're going to learn how to use properties of rational exponents to simplify expressions with rational exponents. All right, great. The word simplify is a big umbrella term for what does it mean to simplify now? We'll talk about that. And use properties of radicals, simplify and radical expressions in simplest form. So I was getting into that when we talk about conjugates and simplest form and combining like radicals. All that stuff really has a lot to do with that second one. Okay, first of all, properties of rational exponents. Let's look at this big table right here as I move my big face. So, the properties of integer exponents you've previously learned can also be used to apply can also be applied to rational exponents. So all these things here can be applied to those. And rational exponents, remember, means fractional exponents, okay? To the 2/3 power, to the 1/2 power, things like that. When you multiply two powers of the same base, you keep the base and you add the exponents. I'm not getting deep into the why as to what that is, but notice even with fractions, it still works out. 1/2 plus 3/2 is 4/2, which is 2, so 5 squared is 25. That means that this times this is 25. All right, so that works out. Right, these are things you can do without a calculator and work them out in that way. Power to a power results in the product of those two powers. We saw a couple things with those in the last section. 3 to the 5/2 squared. 5/2 times 2 is just 5, so 3 to the 5th is 243. A product raised to a power means that you raise both factors of the product into that power. So 16 times 9 to the 1/2. Maybe you don't know what 16 times 9 is, although it's 144. But maybe you didn't know what it was, or it gets something that's too big. Instead, raise them both separately to the 1/2. And remember, 1/2 means square root of. And so square root of 16 is 4, square root of 9 is 3, 4 times 3 is 12. You can work in either or fashion. Remember, this is all about creativity. Does it make more sense to split them up? Does it make more sense to join them together? Depends on what the question is and what you're being asked to do. Negative exponents can be written as positive as long as you put it in the other side of the fraction. If it was in the numerator, it goes in the denominator, and vice versa. Denominator goes in the numerator. A can't equal 0. If it did, you'd be dividing by 0. So this A is not 0. We saw this literally in the last section, so I'll just move on from that one. They're just showing how it applies to fractional exponents, though. Anything to the 0 power is 1, provided we're not talking about 0. We don't talk about 0. 213 to the 0 is 1. When you're dividing powers of the same base here, you keep the base and you subtract the exponents here. And again, A can't equal 0. So you subtract these. 5/2 minus 1/2 is 4/2, which is 2, and 4 to the second power is 16. Notice the 4's do not divide. They don't cancel, they don't divide, they don't reduce, anything like that, because you're dividing certain amounts of 4 from here. That's where it's being applied. The division's happening. We're just doing it through subtraction of the exponents. And lastly, power of a quotient. Right here, a fraction raised to a power. You can raise each part to the power. Denominator cannot be 0. So same thing here, 27 over 64 to the 1/3. Let's raise both of them to the 1/3 separately, which is taking the cube root, and you get 3/4 as a result. So those are examples without actually being the examples they're going to talk about here in just a moment, because they're going to possibly do a lot of them at a time. I wish that they kind of put these ones right next to each other. Excuse me, not that one. This one right next to, say, this one right here. So it's all about keep the base and either add or subtract the exponents. And then this one right here, let's see, the power of a product and power of a quotient right next to each other. I like those ones next to each other as well. Okay, so some examples of this. And again, this isn't new except the fact we're using fractions, and you have to be comfortable in your fraction work. That also includes common denominators and, all that sorts. A lot of examples here. They're written straight out as results of what you do, and we can see how they operate in some creative forms, maybe. Here we have to add exponents. 1/4 plus 1/2 is 3/4. Why? Because 1/2 is 2/4, and 1/4 plus 2/4 is 3/4. So did they do more after that? Doesn't look like it. Their end result is just making sure that they have it in that form. I can see why they might get 7 cubed and then work on its 4th root, but its 4th root can't be simplified more. We're not trying to work in the calculator so much on this, if that makes sense. 6 to the 1/2 times 4 to the 3/2 squared. To begin with, you can't really do much with these two things together. You can't turn 6 times 4 into 24. PEMDAS, order of operations, says you must deal with the exponents first, and they don't have the same base. So we do deal with the exponents first, but you can't take the square root of 6 or cube root of 4, naturally. They're not perfect squares, perfect cubes, things like that. But the squared is on the outside, and we can deal with that. So we square 6 to the 1/2. We square 4 to the 1/3. And if you notice, 1/2 times 2 is 1. You're left with 6. 1/3 times 2 is 4 to the 2/3 power. So the 6 remains the same. 4 to the 2/3 power doesn't simplify more, and you can't do any more beyond this. Remember, order of operations. 6 needs to stay separate from the 4. And it keeps going, so on and so forth. Let's see more on this one. Same thing. Even though they have the same exponent, that actually means nothing with respect to the bases being different. So different bases. However, what you can do is take this property where it shows them as separate things, and it does allow you to do something with them. You can condense them into 1. You can do 4 times 3 raised to the 5th power like this and turn it into 12. And now you can do 12 to the 5th like that. So there are things you can do as long as you see it that way, get that perception. And negative exponent turns into a fraction as a result. Not the exponent, the base. 5 is also 5 to the 1st power is what they're showing there. You're doing 1 minus 1/3 when you divide the bases, and 1 minus 1/3 is 2/3. So you can see a lot of fraction exponent results. This is part of our simplification process. And lastly, same thing here, 42 to the 1/3 over 6 to the 1/3. These can divide provided that you pull that 1/3 out and raise them both to the 1/3 that way. 42 over 6 is 7. And 7 to the 1/3 squared, you do the 1/3 times 2, you get 7 to the 2/3 power. So interesting way that they're writing some of those ones as results with fractional exponents. Those are accepted answers if you can't simplify it more. All right, simplifying radical expressions. Now, we've done these with square roots before, so we can say, hey, it works with any root. With any root, we can do it. So I'm just going to go kind of fast through these ones. When you take the nth root of a times b, you can split it up, or you can merge them together, right? It's an either or. Do you want to go this way? Do you want to go that way? It's based on the problem. In the example, you can see that they're split up, and there's good reason to merge them together here. Cube root of 4, I don't know. Cube root of 2, I don't know. When you multiply them, if you multiply 4 with 2 to get 8, when you merge them as one product, you do get 2 as a result because the cube root of 8 is 2. So it ends up cleaning up. And same with nth root of a quotient. You can split them up that way or rejoin them depending on what it is you're trying to look to do again. So they're split up right now. I don't know the 4th root of 162. Don't know the 4th root of 2. But when you divide them with under the same 4th root hat like this, you get 4th root of 81, which of course is 3. So, they're really asking you to be clever in working these things out in such a way that, as I'd state, we can give you these, right? You can have access to them all you want, probably even on a test, right? They're right in front of you. Maybe, maybe not. I don't know. But the question is, do you know what to do with them? Do you know what to do with them? Do you know how to strategically work around what it is? And sometimes it's just playing with your numbers. I didn't do the problem set yet. I don't know how it is I'm going to play with the numbers, but we'll give it a look. All right, some more examples of that. Once again, you just saw what it was above. 12 times 18 is 216. Cube root of that is 6. Divide those, you get 16. 4th root of that is 2. So more of the same from there. All right, next set. An expression involving a radical with index n is in simplest form when these three conditions are met. No radicands have perfect nth powers as factors other than 1. That's a way of saying that, I'm kind of bad at reading out exactly what that thing says, but basically you have fully taken everything out of the radical that you could have, all perfect powers. No radicands contain fractions. You cannot have a fraction within some sort of thing right here, right? Because that means your denominator is irrational. You're going to have to rationalize it if that happens. No radicals appear in the denominator of the fraction, and that's kind of the same thing as that right there, because whether you have it joined like this or separated as two different ones like that, they both represent the same thing, which is irrational denominator. To meet the last two conditions, you got to rationalize, okay? So we'll talk about rationalization, but not just of square roots. They're also that of cube roots and all that, and fifth roots. Write the expressions here and here in simplest form. When we take the cube root of 135, it's like taking the square root of 135. You want to find perfect squares that exist in your number. Maybe there are perfect squares in 135, maybe not. I think 9 works. But here, you got to find a perfect cube within 135. Your perfect cubes involve, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, etc. So you got to factor perfect cubes out of there. They found 27 as a perfect cube. It is. 135 is 27 times 5, and cube root of 27 is 3. So instead of saying 3 root 5, we're going to have to say 3 times the cube root of 5, and that's the result. This one here, the issue is you can't find perfect fifth power values within, but the denominator is irrational, so we're going to have to rationalize it. Now, there are a couple ways you can talk about it and work this thing out. Depends on what you go for. In this case, what you want to do is multiply by something big enough so that you can end up taking its perfect fifth root of something. So, 2 to the fifth power is 32, 3 to the fifth power is 243, 4 to the fifth power is 1024. These end up becoming pretty big numbers for perfect fifth power values. The smallest perfect fifth power value you can find in this case is 32 if I do 8 times 4. That means you have to do this number times 4 as well. Keep in mind it's got a fifth root inside of it. Now, if you want a different appearance of this, as they're breaking this down, by the way, fifth root of 32 is 2, and then you end up getting that result. If you want to see a different appearance of this, and I will probably not do these in the other problems, but it would be this. You take the fifth root of 8. Now, 8 is also 2 cubed. You might say, hey, I want to make sure that I multiply by something where this exponent ends up being a 5 with this base. That means this would have to be a 2, right? This would end up getting the fifth root of 2 to the fifth power. That's your goal. That's your goal in that scenario, which ends up being 2. Well, 2 squared is indeed 4, so that's where that number can also come from, and you can see it. So that's one version of it. If you don't know your perfect fifth power values, break this down as an element to raise to a smaller power and see what you can do from there. I'll probably be fine and not be using that for the most part. For denominator, that is a sum or difference involving square roots, multiply both the numerator and denominator by the conjugate of the denominator. So you have expressions here that are conjugates of each other. It's a plus, b, a plus and a minus, like that kind of thing. As long as it's the same thing, a root b plus c root d times a root b minus c root d, all the irrationals will cancel out in a way where it will become this squared minus this squared. Now you have to work some things out in that way. Not everything has to have irrational components, but this can have as many as these many irrational components, and you're going to have to do that to rationalize it. So 1 over 5 plus root 3, to rewrite in simplest form, you can see this is irrational. Multiplying by root 3 over root 3 won't do the trick because it would distribute into both terms, and even though this would rationalize, this would not, so it would be a hiccup. So what we do instead, and squaring it doesn't help either, and changes your number. What we have to do is multiply by its conjugate. 5 minus root 3 over 5 minus root 3. This part ends up becoming a difference of 2 squares, which is a squared minus b squared, or 25 minus 3, which is 22. On top, 1 distributes into these, and of course 1 times anything is just that number, so here's the simplified version. See, we rationalize the denominator. The number itself is still rational. There's nothing we can do about that. But now that we've simplified it in such a way that we've put it over 22, a whole number, that ends up being the result we want. If something can reduce in the fraction, we'll go ahead and do that. I'm not expecting that from these problems. Sometimes they just get you to do the practice. If I work creatively enough to make a problem that gets you to reduce fractions, or if I run into that, I'll be sure to tell you. and possibly the last thing, I don't know if it actually is, but radical expressions with the same index and radicand are like radicals. Index is what I call the root, the fourth root, like that index. The same radicand means the number inside of the radical, so these ones right here. So 4th root of 10 and 4th root of 10, they're like radicals. I'll probably just say like terms, combine like terms. So it's just like if these were x's. What if this said x plus 7x? We know that's 8x because of the concept that you can factor an x out of both terms. You're left with 1 plus 7. And that 8 times x gives you 8x. And same thing here. They're showing you on this question. Root 10 plus 7, or 4 root 10, 4th root of 10, plus 7 times the 4th root of 10. You don't have to do the factoring stage. We're just going to combine like terms, add the coefficients. 1 plus 7 is 8. You're left with 8 times the 4th root of 10. And same with this one right here. 2 times 8 to the 1/5 power plus 10 times 8 to the 1/5 power. And as a reminder, you can't do 2 times 8 and 10 times 8 here because of what they're raised to by PEMDAS. But you can do the 2 plus 10 to get 12. And this last one, these are not alike. So can you not do anything? Well, you can't combine these as they are, but you can simplify. The cube root of 54. The cube root of 54 can be simplified to the cube root of 27 times the cube root of 2. Cube root of 27 is 3. So you turn it into 3 times the cube root of 2 minus cube root of 2. Remember, that's a 1. 3 minus 1 is 2. You get 2 times the cube root of 2 when you're simplified. So like I said, there's quite a bit that can be talked about in being creative with this stuff. Oh, it looks like there's still more to do. Yeah, it just doesn't stop from there. Okay, the properties of rational exponents and radicals can also be applied to expressions involving variables. Ah, that's right. This is involved here. Because a variable can be positive, negative, or 0, sometimes absolute value is needed when simplifying a variable expression. Now, I'll kind of trying to remind you of what this is about in a second. When n is an odd number, cube root to the 3rd power, things like that, they can cancel out and you're just left with x. Whether x was positive or negative, it stays as positive or negative as a result. You see, the 7th root of 5 to the 7th is 5, and the 7th root of 5 to the negative 7 is negative 5. You can take an odd root of a negative number, and when you raise a negative number to an odd power, it is negative. So both of those together culminate in a negative version of that value. However, in this case, when n is even, the nth root of x to the n power is the absolute value of x. Now, this is because whether we raise 3 to the 4th or negative 3 to the 4th, they both turn positive. And so when you then take that 4th root after that, you do indeed get 3. So you have to understand that, whenever we solve an equation like x squared equals 9, and then we take the square root of both sides, we say x equals plus or minus root 3. And that is the answer because, once again, what can you square to get 9? 3 or negative 3. There's a step that we skip in the middle. The square root of x squared, we skip this step. We say is the absolute value of x. Listen, the square root of 9 is 3. But what we don't do on this side often is this intermediate step. Let me use a different color. What we don't use here is an intermediate step right here. We often just skip it and go move on forward. But if you know anything about absolute values, the condition met here is if the absolute value of x is 3, x either equals positive or negative 3. And that's the portion where we're seeing that the square root of x squared is indeed the absolute value of x, given that this was a second root, an even root, and an even root that's going to happen. Now, absolute value is not needed when all variables are assumed to be positive. So if they assume all variables are positive, then in this case, the square root of x squared is just x, because it's just a positive number. We don't care about the negative result. We'll see what they ask us to do in one case or the other. I don't know if they will separate. So let's see some examples of that, simplifying each expression. Now we have variables involved, and there's a lot of work that can be written within. Hopefully we can just talk about how it works, and then when I do the problems, I can just do them that way. The cube root of 64, y to the 6th, they're kind of doing a lot within here. I don't generally do this with my numbers turning it into 4 cubed, for example. Cube root of 64, I would know is 4. I ask what number do I cube to get 64, and I'll say 4. So anyway, what I do, though, is I do treat them separately, like cube root of 64 times cube root of y to the 6th. I might not write them separately, but I do treat them separately. Cube root of 64 is 4, and we have to work on this part. Now, what they're doing here is pretty interesting of note. And again, your teacher might teach it this way if they work it out of the book. I'm less inclined to do so because it looks very busy. It looks, all that. I'll show you another way. But they turn y to the 6th into y squared cubed. And they do that so they can cancel out these cubes right here. Cube root of something cubed is just that something, right? It's just that y squared. So the radical portion is gone as well, and then you're left with 4y squared. What I do instead, and I treat it this way, I don't write it this way often, but I might with you guys a little bit. If you recall from the previous section, what we can do here is rewrite this as y to the 6 over 6 thirds power. and 6 divided by 3 is 2. You are dividing this number by this number. Now, there's more you might have to do with these ones. That is getting y squared, by the way. You might have to do a little more with those ones, all depending on whether, like if it says 7 divided by 3, well, now we have to talk about remainders and stuff like that. I think they're going to do some of these problems down below. But that's kind of an example of that. Fourth root of x to the fourth over y to the eighth. Again, you can treat them separately by splitting them apart. Their own separate fourth roots, different variables for different things. Fourth root of x to the fourth, you're dividing 4 by 4 and you get 1. So you just get just x to the first power. The difference in this question is this is an even root of something to an even power, that kind of thing, when this is even. So we do have to put the absolute value around it because who knows if this number is positive or negative. We have to treat it as such either way. Now with this one here, we have 8 divided by 4, which is 2. Now you might be asking, why don't we put this one in absolute values? Well, I'll say that you could. There's nothing wrong with doing it, but it becomes a redundancy. How come? Because this y is still squared. And what happens when you square a negative number? It still turns positive. So we don't worry to do it unless when we're dividing, it ends up being, well, an odd power, I should say. Something that was even and turns odd, like when it turns to the first power. Then you have to put the absolute values in that case. Now, this other set of examples does say write each expression in simplest form, assume all variables are positive. And I think that's because we're going to be dealing with ones that have fractions in it. So they don't want to run into that mess when they are negative in what we talk about there. So this time we don't have to worry about absolute value bits. Remember, there are 82 questions here. So my goal is to do as much drill and kill as possible with these when I can. The fifth root of all of these. Okay, once again, I would treat them all separately. For example, and they're writing things, and all the things they're writing are great, and I'm going to talk about what they kind of did as a result of this. But the fifth root of 4 is among these things, and you can see that the fifth root of 4 remains in the final answer. You know why? I can't take the fifth root of 4. The smallest whole number I can take the fifth root of is 32. I mean, nothing else lower than that. Fifth root of 31, fifth root of 16, none of those will do anything for me. Now I have the fifth root of a to the eighth. Now what you're going to see them do in this is they're going to separate this into the fifth root of a to the fifth times the fifth root of a cubed. The reason, and then they're going to split them apart, literally. They're going to place them in two different fifth power radicals. Do you literally have to do that second term the second step right here, or even the step? No, but what they're going to do is take the fifth root of a to the fifth. Why? Because 5 can divide by 5. 5 divided by 5 is 1, and you're left with a. Remember, there's no absolute value in that a because we're assuming the variable is positive. Then we also have the fifth root of b to the 10th. Now, 10 divided by 5 is 2. So you're just left with that b squared, and that pulls out in the outside. Oh, I'm sorry, it's 14th. I was looking at its lower step. The fifth root of b to the 14th. Now they split up 14 into b to the 10th times b to the 4th. And keep in mind the exponents are adding in these cases. Now, how come they're pulling out a 10 and not 5? How come they can't do 15? 15 is larger than 14. 5, it's not going up to 15. It's going up to 14. Why not 5? Because 5 can go into 14 twice. This is actually literally just a division. You'll see me do this as more as 14 over 15. 14 divided by 5, I should say. 5 goes into 14 twice, and there's a remainder of 4. So the twice that you can see appears here. The remainder is here. Why does the 4 remain inside? Because 4 can't divide by 5 and get any more quotient whole numbers back out, right? You can't take the fifth root of b to the 4th, just like you can't take the fifth root of 4. It's not a perfect fifth power value. C, on the other hand, this is c to the 5th, and 5 divided by 5 is 1. So you see that last c value over here. So there's a lot of work that's to be had, and like I said, they're writing different work than I'm going to. If you want to follow along with me, that's up to you. Your goal is to get the right answer, so if you want to try it and compare to my work, fine. If you want to hear the way I talk about it, that's completely up to you. That's part A. I'll go a little faster now. Part B, we have x over the cube root of y to the 8th power. Now, this is one of those things where you can choose to either rationalize denominator first or simplify the radical first and rationalize what's left. Looks like they're going straight into rationalization. So they're going to multiply this bottom part by something that you can divide by 3, basically. If I get an extra thing, if I can turn this into y to the 9th, then I'll be good. So I just need to multiply by an extra cube root of y. So that's what they're going to do. Times cube root of y on top and bottom rationalizes it because this turns into cube root of y to the 9th, and 9 divided by 3 is 3, so you get y cubed. This is x times cube root of y on top, and then you're good and simplified right there. Remember, these y's can't do anything like cancel out or anything like that. This is a cube root of. And if you ended up doing subtraction or something like that, you just end up getting right back where you started. So it's best that you leave it like this. And the last example here, you have 14xy to the 1/3 over 2x to the 3/4 z to the negative 6. I know that's a lot that's involved, and even what they wrote looks like a lot as well. That looks like a nightmare to go with. There's not much you can do to make this a lot easier. Depends on how much you want to split things up. One thing I can see for sure, I have 14 divided by 2, right? Well, 14 divided by 2 is 7. Remember, it's not 12. We're not subtracting. It's division. 14 over 2 is 7. Okay, that's part of our result. We have x to the first over x to the 3/4. Think about what we're going to do there in just a second. And we have y to the 1/3 all on its own. I guess that stays as it is. Now, z to the negative 6th, what I tend to do with these is I tend to turn it positive as soon as possible. When there's a negative exponent in a fraction, I will turn it positive. How do you turn it positive? You move it into this other part of the fraction. So it becomes z to the positive 6 in the numerator. Your final answer, you're also going to see, has z to the 6 in the numerator. Heck, there is no denominator anymore. You're just left with the numerator value. X to the first over x to the 3/4 is 1 minus x to the 1 minus 3/4 power. 1 minus 3/4 is 1/4, so you're left with x and a quarter. X to the 1/4. You have y to the 1/3. So ultimately 7, x to the 1/4, y to the 1/3, and z to the 6 is all that's involved. 7, x to the 1/4, y to the 1/3, z. And that's the answer that we, z to the 6, I should say. And that's the answer that we have right here. Okay, we still have to add and subtract variable exponents, so I guess there's not much different from what we had, or variable expressions with radicals. It's not much different from what we had before as long as we have like terms, and these are like terms here. 5 plus 6 is 11, you get 11 root y. And in this last example here, these aren't the same, but we can make them the same. In this case here, I would turn, let's start with that cube root of 54. That's cube root of 27. We saw this already, times cube root of 2. They get a lot of cube root of 27s, which is 3 times cube root of 2. So understand that that 3 gets to multiply with anything out in front, such as that z. So what you'll end up having is that 3 with that z right there, right? Now, in this part, you have z to the 5th, and you have the cube root of that. So you can pull out a full z cubed out of that, take its cube root, you get z. It's like 5 divided by 3. 3 goes into 5 once, and what remains are 2 z's inside of there, like that. So you end up getting 12, you get 12z times the cube root of 2z squared minus that 3 that pulls out, 3z times the cube root of 2, the 2 stays inside there, z squared. Now these two are the same right here, and now you can combine like terms, 12z minus 3z to get 9z. So you're now left with 9z times the cube root of 2z squared. This might all sound very complex, but as you understand, I tried to do as much as possible and still stay within a half hour, so it was still very long. We still have a long ways to go. We're done with the lecture portion. We're going to start with the vocabulary and core concept check, and then we'll have 80 other problems to do on top of these two, so 82 in total. So buckle in, and we'll see what I can do. I'm going to go mostly under my guys, under my processes and things that I think will help speed things up for myself. All right, writing. Number 1, how do you know when a radical expression is in simplest form? Basically, you have all perfect, let's see, I don't know how they said it in that technical way, but basically the denominator is rationalized is something I'm going to say. The denominator is rationalized, and you have all perfect powers removed from radical. So my way of saying that is basically you can't take any more roots of that number or that variable, even when it's raised to certain powers. That's just not possible within there. So I know that's not the best answer. They have something written over on the other side here. You can read it again and see if you can make sense of it. It's this set right here, simplest form. But in terms of rationalizing a denominator, I am implying, of course, when you have something like this, right here, that also is an unrationalized denominator. This is irrational. This is cube root of 4 over cube root of 5. So that's another instance of it. All right, number 2, which one doesn't belong? Which radical expression does not belong with the other 3? Explain your reasoning. Okay, so this one, if I call that A, all I would say for now that I know is that that has an irrational denominator, so it's not simplified. I'd assume the other 3 are simplified, so they are probably the different B's, because there's nothing else I can pull out of here. Square root of x, I can't do anything with. 4th root of 11, no. And 5th root of 9x, This isn't square root, so I can't do anything else with these. These two have variables, so it's nothing about that. These are odd roots, and that's even, and that's odd. I'd say it's probably this one. This is not simplified because the denominator is not rationalized. So that's where I'm still talking about this right here. Denominator needs to be rationalized. Okay. Anyway, so there is that, guys. We're going to start with the problem set numbers 3 through 82. So buckle in. I hope that everything that I say can make some sense. I do want to state one more time that several things. Number one, as I just stated, what I just stated there. Number one, everyone teaches this differently. What the book does is going to be different than how I write things. I'm not going to follow everything in their process in that way. Number two, that's kind of how I just want to say that next part. You can solve each problem differently, simplify each problem differently. Even I can. Even I'll think about certain problems differently. Say, I might want to do this or I might want to do that. I'll try and stick to one as often as I feel that that's natural. Number three, really within strategy, is even if you had the properties in front of you the entire time, that doesn't guarantee that you can get all these ones right all the time. You still need to be creative for yourself in finding a way to go about it. So I'm going to find that way to go about it. I know the properties. I'm going to find the way to go about it and be as creative as possible with every which problem. Okay, so we are going to start on non-variable ones. We have exercises 3 through 12, where we are going to use the properties of rational exponents to simplify the expression. Now, what you've possibly noticed is that they have been okay with writing these answers as fractional exponent values, despite the fact that I feel like there's more that I can do with them, and I sometimes almost want to, but they're just talking about using the properties themselves. So 9 squared to the 1/3 power equals 9 to the 2 times 1/3 power, which is 9 to the 2/3 power, like that. Now, once again, there's more to this problem that I personally would want to do. If I were to do more on the side, and I don't think I'm going to do this for future problems because they're not really having us do it, well, I don't know. I kind of want to do them for our practice. This is 9 squared. Well, this is 9 squared, right? That's 81. 9 squared is 81, and we're taking the cube root of 81. And the cube root of 81 is the cube root of 27 times the cube root of 3, which is 3 times the cube root of 3. Now, I think they're just looking for this. That really seemed like that's all they were going for. But this is also equivalent to it, and that's something we're expected to be able to do later. That's why I'm kind of bringing it up. Number 4, we have 12 squared to the 1/4 power. More of the same as the previous property. This is a power raised to a power, or power of a power is the way that they say it. So this is 12 to the 2 times 1/4 power. 2 times 1/4 is 2/4, which is 1/2. So that means that's the final answer. If I were to expand more on this thing, that's also the square root of 12. And you might know the square root of 12 is root 4 times root 3, or 2 root 3. Again, if we were to do full simplification, that's what actually I would be looking for personally. But what I'm writing in black is the probably textbook answer. Number 5, 6 over 6 to the 1/4 power. I think it's at this stage when these numbers get a little bigger that I'm going to give up on saying the other things I was saying. So 6 over 6 to the 1/4 power. Now we probably just want to advance forward. This is 6 to the 1st power over 6 to the 1/4 power. So we're going to do 6 to the 1 minus 1/4 power. Now 1 minus 1/4 is 3/4, so that's 6 to the 3/4 power. And like I said, I'll just leave that one be. Otherwise, 6 cubed is 216. Find a perfect 4th root number that can divide out of 216. I don't know which one it is. That's why these problems are probably left for you to just practice the exponent work. Now, the reason we can do what we did on this one is because the 6's were the same base, and that's going to be true for number 6 as well. On number 6, we have 7 over 7 to the 1/3 power. Remember, that means 7 to the 1st, so this is 7 to the 1 minus 1/3 power, and 1 minus 1/3 is 2/3, so 7 to the 2/3 power goes here. Again, because 7's are the same base, you can keep that base as you subtract the exponents. Okay, number 7, we're dealing with a couple of properties here, and it depends on how you want to work out and write these things. I have 8 to the 4th over 10 to the 4th raised to the negative 1/4 power. Like I said, more than one way to work on this. If there's one thing I wanted to do first, and I don't know if you're aware of this, I can turn the negative exponent positive right now to 1/4 if I flipped the entire fraction, because this would go down and this would go up to turn them positive. In this case, this now turns positive here. This turns, you'll say they were positive. Yeah, but I induced the negative into here and then flipped them. Now this is a positive exponent. Now, we're not looking to do 10 to the fourth and 8 to the fourth, not at all. But what we could do is we could reduce 10 over 8 if we did turn this into the fourth power as a whole, and that all is raised to the 1/4 power. That's an option. In which case, then 10 over 8 reduces to 5 over 4. And the 4 to the 1/4 power, like that, is also 4 times 1/4, which is 1. So 5/4 to the first power is 5/4. And there's the final result. An alternative you could do is you could do the 1/4 power thing right now into both of these separately. So you'll get 10 to the first over 8 to the first, and then that's 10 and that's 8, and then you reduce the fraction. Our goal is never to raise 10 and 8 to the fourth power separately, though. So even though, like I said, there's more than one way to get an answer, that's really the only answer they'd be looking for, and I'd agree. So number 8 is more of the same. Maybe let's do this one that opposite way. Maybe even this time we'll take care of the negative later. So let's do this in kind of a different format this time. This time, let's infuse that negative 1/3 right now. It goes straight into these ones right here, where it becomes 9 cubed to the negative 1/3 power divided by 6 cubed to the negative 1/3 power. Okay, like that. Which means the 3 multiplies by negative 1/3 on both of these. Like that. 3 times negative 1/3 is negative 1 on both of those. And you have to turn these exponents positive. That's part of our simplification process. In order to do so, like I said, in a fraction, they go in their different spots. Numerator goes to denominator, denominator goes to numerator. Now this becomes 6 over 9, which reduces to 2/3. That's just but kind of an opposite way of doing what we did this first time on number 7, how I treated the negative exponent first. Here it looks like I really treated it last, and how I kind of applied the exponent into both of these first before kind of not factoring it out, but writing it on the outside. I'm going to keep reminding you that there's more than one way to do these problems, and I'm trying to give you alternatives where you can. In fact, when you look at these, 3 looks like 4, 5 looks like 6, 7 looks like 8. So with 9 and 10, maybe we can find 2 different ways to do these, all depending on what's written. Number 9, we have 3 to the negative 2/3 times 3 to the 1/3, all raised to the negative first power. When I see the same base, I'd like to do something with those exponents as soon as possible. Simplify the inside before taking care of the outside, meaning the negative 1. So maybe we do something like we add these exponents, negative 2/3 plus 1/3. Again, because the bases are multiplying, you keep the base and you add the exponents. Negative 2/3 plus 1/3 is negative 1/3. So now you have, that's still on the outside, now you have 3 to the negative 1/3 on the inside, and you have negative 1 on the outside. Do you want to flip this fraction now? I think I'd now rather deal with this negative exponent as a for sure. This goes inside here. Now you have positive 3 to the 1/3, and then you're done. So instead of a double flip, you're just multiplying these. Now, remember, these do multiply, power to a power. And what you'll start to see me do more of is when you see a property more than a couple times, I'm going to kind of skip steps in that property. Now that we've seen power to a power several times, I feel like I just want to multiply them without needing to write multiplication, unless there's more work I need to show, especially in the case of fractions. And it looks like they're really doing a lot with fractions. This is how they're separating these from what you did in IM2. We barely dealt with any fractions, if any at all, in IM2 in these cases. Now, you also see me in some cases, right? All right, this is the cube root of 3. I personally like to see numbers and stuff with their radical versions, but it looks like the book's all good with these other answers. All right, so right here, you know, what you can do on these ones is last time we got these together to add the exponents, maybe let's put the negative 1/4 in play right now with them. This isn't generally something I do, but there's nothing wrong with it. So this is one where we're doing a different kind of property, so I'm going to show you. The negative 1/4 will multiply by the 1/2, and it'll multiply by the negative 3/2. So you'll get 5 to the negative 1/8. That's where those multiply. And then you have 5 to the positive 3/8. 3/8. So that time I put them right there like that, and this becomes 5 to the negative 1/8 plus 3/8 power like that, which is 5 to the 2/8, which is 5 to the 1/4, or 4th root of 5. I'll just leave it as 5 to the 1/4. So once again, it's hard to just say that there's only one way to do a problem, right? There clearly is not. I'm showing you different versions just within this set right here, and I hope you're finding your little niche on what will make it easiest for you. I don't know what is and what isn't. For me, it's really dependent on a lot of things. Do I have negative exponents or not? Do I have a fraction or not? Am I dealing with numbers versus variables? A lot of these problems I honestly probably do in one step in my head versus what I got to show you here in these stages. Oh, there's so many things I can do with this problem, and I don't even know where to begin with it. Oh man, where do I begin with it? Okay, so where I want to begin with this is when you look at these, you're saying, well, these are all different bases, and dividing and multiplying, you can't really do anything with them. I guess one of them that I'll do is what the book would have likely done, which is because they're all to the 2/3 power. Let's just do the numerator first. A product, power of a product can be split into a product of 2 powers. Because it's a product of 2 powers, it can be merged into a product raised to that power like that. And because this quotient is also raised to that same power, you can actually write them all as one single thing raised to that power. So here's probably the book's version of here's what I would do. 2 times 16 is 32, and 32 over 4 is 8. So you get 8 to the, to the 2/3 power. 8 to the 2/3 power. Now this is one that I hope they're not boxing this one, because you can take the cube root of 8. You can take the cube root of 8. Cube root of 8 is 2, and 2 squared is 4. So we should just be writing 4 as that answer, not 8 to the 2/3, despite the fact there in that problem that you have a fractional exponent. The reason we left the other ones as fractional exponents is because, well, you couldn't do anything with them in full effect, right? So this one I feel like we could. Now number 12. I'll try and do a different version on number 12 from what we just did on that one. Now both of these numbers are 49, so there's something we can do with those. And by the way, these are different exponents, so it seems, so we're gonna have to work something off that, unless you got a common denominator, of course. So I'm gonna start with this, keep the base, add the exponents. Let's just leave this one alone on bottom for a second, like that. 3/8 plus 7/8 is 10/8. Oh, that's what happens. This fraction reduces. 49 to the 10/8 power, which reduces to 49 to the 5/4 power. Excuse me, 49 to the 5/4 power. And this is over 7 to the 5/4. Okay, so now they're the same, right? So what you could do, you could kind of put them as one fraction to the 5/4 power. That's fine. Let me show you an alternative of this. You could turn 49 into 7 squared. And the reason why we do that is because now this 2 can multiply by 5/4 and become 10/4. And this becomes 7 to the 10/4 over 7 to the 5/4. And now they have the same base, and you can take those and subtract the exponents. So that becomes 7 to the 10 minus 5 is 5/4, like that. So that's a version. And remember, the other version, like I stated, is you can take these, raise them both to the 5/4 power, just in one way like that, and 49 over 7 is 7. You get 7 to the 5/4 that way too. Kind of up to you, but I'm showing you different versions of what there are. I'm not going to stop saying that. As long as I keep showing you different versions, I'm not going to stop saying that. All right, and exercise is 13 to 20. Use the properties of radicals to simplify the expression. Okay. Now, this time, we're going to have to do some actual simplification within here. Kind of like what I did on numbers 3 and 4 to start with, really breaking it down. We're going to do the same thing here. Square root of 72, because it's square roots, we've done these ever since IM2, probably even some to start in IM3. That's root 36 times root 2, which is 6 root 2. Now, root 2 times 6 root 2, understand that there are 2 root 2's multiplying. This isn't a like terms kind of thing. You are actually doing 6 times root 2 times root 2. And the square root of 2 times square root of 2 is 2. So this is 6 times 2, which is 12. That's a lot more work than you're going to see me write in other problems. I'm probably going to go next time straight from here to here and straight from there to there, because those things are grouped up right then and there to work that out. Number 14, well, it depends, because now we're dealing with cube roots, so we have to make sure that we get our first hit of cube roots the right way that we understand. Cube root of 16 times cube root of 32. One thing I want to make mention of, and this is true for this problem as well, by the way, here's an alternative of what we could have done before I continue on, is root 2 times root 72. We could have turned them into a single square root, and that's root 144. And square root of 144 is 12. And you go, oh, that was a lot easier. Sure, if you knew that it would be a perfect square value. If you didn't, you're just making a bigger number out of that. It's easier to make smaller numbers out of it if you can. Likewise, I can do 16 times 32, get 512. And if you know the cube root of 512, which is a perfect cube, then you get your answer. But if you don't know that, let's work off of these other properties here, and then I'll go back to that one and see if which one you prefer, which one you think you know more, assuming you didn't have a calculator. Now, cube root of 16, it's not like square root of 16. It's not 4. You have to break this up into perfect cubes. If 8's a perfect cube, 2 is not, but that's all you could do with it. 32 also has 8 as a perfect cube there. And then that's also times cube root of 4. Now, when I multiplied, not when I multiply, but these two cube root of 8s are 2. So I'm going to write them as 2 times 2. Now, these two are under the same cube root hat. It's at this point that you must simplify by writing them inside that same hat together. That's a 2 times 4 inside there. Cube root of 2 times 4 is 8. So outside you have 4. Inside you have cube root of 8. We just saw the cube root of 8 was 2. So that's 4 times 2, which is 8. Should probably write some equals here, 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 stuff like that. So that equals 8. Alternatively, what did I state? You could also do cube root of 16 times cube root of 32, which is cube root of 512. Cube root of 512 is no doubt 8. Was that faster? Sure. But was it also a perfect cube? Yes. Did you know that it was? Not necessarily. You still have to also multiply that to get there. So that would take a while, all depending, and it's good to practice these when you have to do it. All right, number 15. Fourth root of 6 times fourth root of 8. This is an example of where you might want to do some multiplication, and I'll talk about why. So in this case here, you can't take the fourth root of 6 or fourth root of 8 or anything like that. There is no, the smallest fourth root power you can factor out of something is the fourth root of 16. Okay, 2 to the fourth is 16. So the fourth root of 16 being 2. These numbers are smaller than 16. So the first thing you are going to want to do this time is actually multiply these ones together, make it a bigger version of something, and then start breaking this one up. So 48, like I said, find a fourth root, perfect fourth root, like 16, that you can break this up into. So instead of 6 times 8, we'll turn it into 16 times 3. And then here you'll get fourth root of 16 is 2. That's 2 times the fourth root of 3, like that. Now this time it wasn't a perfect fourth power value, unfortunately, and thankfully this number was small enough you could work it out this way. What you could also do as an alternative, this is kind of being a little bit clever with it. You turn 6 into 3 times 2. The reason why we would turn it into 3 times 2 instead is because now we can instead inherit the 8 with the 2, like that. And then here you get fourth root of 16. And you can see there's that fourth root of 3. I'll just write it on this side. And then you still get to that same answer, right? Fourth root of 16 is 2 times the fourth root of 3. So you can cleverly work that around in a different way as long as you get your perfect fourth power value. But that's the goal. You need to know what a perfect fourth power value is in that problem. Number 16, you have the fourth root of 8 times the fourth root of 8. I'm trying to think of clever ways to go about this one as well. Even clevererest than what we just did on the previous problem. You're probably not all about clever. You're like, just give me the answer. Sorry, that's not how we play. Here's the thing. I could even just write it as this. This is the fourth root of 8 squared, right? This is all 8 to the first, 8 to the first. We multiply those. We add the exponents. So I can then turn that into 8 to the 2/4 power, which is 8 to the 1/2, which means we're doing the square root of 8. So the square root of 8 equals root 4 times root 2, or 2 root 2. That would be a final answer. Notice that my fourth root actually turned into a second root, which is a little bit different than we've seen. So let's look at a different version of how to do this problem and how we can make sure that we can turn it into that. This is where the fractional exponent really helped me remind myself that you got to do some reduction there. So what if we multiplied these? We'd get the fourth root of 64. Now the fourth root of 64 can be broken up into a perfect fourth power values. You got 16 and 81. So just 16. Fourth root of 16 times fourth root of 4. And then there you end up getting 2 times the fourth root of 4. Well, that one kind of doesn't really look like the last thing that we got, right? So why is that one different than this one? Because we got to find out how to break that up in a different way and not make it be a fourth root value. So this one ends up kind of hurting you more than it ends up helping you for a problem like this. How to turn it back into 2 root 2? I'm honestly thinking about it now. The square root of 2, let's see, because this is also 4 to the 1/4 power, which is 2 squared to the 1/4 power. which is 2 to the 2/4 power, which is 2 to the 1/2, which is square root of 2. So there's a lot you'd have to work out in that form to get it that way. As clever as I was doing things this way, it actually helped me out more. And I did it because these had the same base. So sometimes some stuff helps you, sometimes it doesn't. You get an answer like this. You're on your way, kid, but you're not quite fully there. And recognizing that is not so easy. I can look at that and say, yeah, I'm done. But I'm forgetful of the fact that 4 is also a perfect square value, and this is an even number. There are just things about that we're going to have to hear in our heads and make sense of it, make sure we don't stir ourselves wrong. Number 17. We have the 5th root of 486 over 5th root of 2. This is one of those cases where it's best to merge them as one single thing here. Now, whether or not you want to write this or you just want to do it's up to you, but the fact of the matter is we can divide these. We divide these and we get 243. 5th root of 243 is actually 3, so I'm going to leave it as that because 3 to the 5th is 243. We're done. Number 18, we have the square root of 2 over square root of 32. Now, just like the last problem, and I didn't state this, but you might say, oh, I got to rationalize the denominator. I got to rationalize. Well, if we do division and fraction reduction, it might work itself out on its own. Because these are square roots, we can divide these. This will turn into root 1 over root 16, like that. And we can take the square roots of both of these. We get 1 over 4, and then we're done. It's rationalized, right? We've taken care of it. Even if I did go to rationalize it, I'd try and simplify root 32 before I actually begin my rationalization process. So we'll leave it like that, as that's the answer. Number 19, we have the cube root of 6 times the cube root of 72 divided by the cube root of 2. It's one of those things, again, where I'd rather not multiply something big if I don't have to. Let's work smaller to begin with. Remember, all of these can multiply and divide together. They're just all under one big cube root, right? But let's make numbers smaller first. Maybe do 6 divided by 2 to get that 3. Cube root of 3 times cube root of 72. And then from there, if you want to multiply, at least they're smaller numbers, you get cube root of 216. Now that's a perfect cube of 6. So we get that. There are other ways you can work off of that. Turn cube root of 72. You can, take an 8 out of that. Cube root of 8 is 2. And then cube root of 9 times cube root. There are a lot of things you can do within there. But like I said, I'm trying to multiply that first. But it did become bigger. It was one of those things I'm relying on it being a perfect cube. If it wasn't a perfect cube, yeah, let's go the other way. If it wasn't a perfect cube, cube root of 72 is cube root 8 times cube root 9, or 2 times cube root 9. And cube root 9 times cube root 3 is cube root 27. Cube root of 27 is 3, and 2 times 3 is 6. Okay, number 20. Excuse me, last one in this set. Let me get a water hit as I write this one. Ooh. Okay. So you have different radicals. I can't divide these unless I get the same radical. And I think it's one of those cases like that one that we saw, especially because these are the same number. Let's work on that bottom. Listen, I'll do the top as well. I'll turn that into cube root of 54. Not the biggest of numbers, so we'll see as that is. But this becomes, right, let's even write it like this. Let's write it like 2 to the 1/6 times 2 to the 1/6. Maybe you can work it off better that way. Then you add the 1/6 and you get 2/6, which is 2/3, or which is 1/3. 2 to the 1/3. 2 to the 1/3 is also the cube root of 2. So, right, when I think they're really asking you, they're begging you to put those together and reduce it there, because now we have cube roots on both of these. So really, there's some cleverness involved. We can divide these now and get cube root of 27, and cube root of 27 is 3. Now again, I haven't seen these problems before. This is my first time working off these, and it's just you gotta find a way. I'm not guaranteeing the way I'm doing it's going to be the fastest or best. Sometimes it might stir me wrong. If I took this other problem right here and got just this right here, I might have even stopped. I lucked myself out in saying, oh yeah, there's another answer, so how can I get there? So we really have to talk about those things as they come along. And I'm only trusting that I'm getting these answers right so far. But, that's the goal, is having a conversation, trying different methods, making sure you still get to the same thing. So hopefully this is panning out for your learning and you're making sense of something, not just, oh, I'm copying this down, I'm getting this right, and he's going to get me the whole way. I can't help you on your test. So these are ones where you're going to have to make sense of what it is that we're doing as a whole. All right, number 21, write the expression in simplest form, fourth root of 567. I'm just going to have to go off the fact that this must have to break apart in some way. Some perfect fourth values I'm going to write out for you. 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth is 256, 5 to the fourth is 625. Now we're already past 567, and these are even numbers. So it looks like 81 is the only one that if we have a shot, we're going to have to work off this one. It turns out that, yes, 81 times 7 is 567. So this can break apart into the fourth root of 81 times the fourth root of, not 3, of 3 is what I'm thinking of for the other part, of 7. And the fourth root of 81 is 3. So you get 3 times the fourth root of 7. And we all good to go, homie. What-cha-cha? Number 22. Fifth root of 288. So they're being daring with some larger powers. Once again, let's come up with what some perfect fifth value numbers are. 2 to the fifth power is 32. 3 to the fifth power is 243. As you can see, we're already going big. 4 to the fifth power is 1024. So they just get massive and fast. Already way eclipsing this. It's more than half that number. Don't even worry about it. 32 is the only number we have a shot with. Is that 32 times 9, I think? So this becomes fifth root of 32 times fifth root of 9. And the fifth root of 32 is 2. So this is 2 times the fifth root of 9. So remember the very first problems they did, numbers 3 and 4? You have to remind yourselves that this is what we're kind of doing now. I mean, I did with rational exponent, but what I was breaking apart down to, probably not what they were looking for yet. They're probably just looking for these. But now we're doing problems like these. Even if they don't have the rational exponents on them, we're still doing that kind of thing. All right, number 23, we have the cube root of 5 over cube root of 4. Or 23, if I said 25, apologies. Cube root of 5 over cube root of 4. Now, if I... See, this would be you playing with something to no avail. If I said, oh, let's divide these. Cube root of 5/4, and that's cube root of 1.25 or something like that. You're like, and I'm done. Actually, there's something with this you kind of, maybe, I don't know if you could. But anyway, we're not doing anything like that, right? These can't divide. They don't reduce. There's nothing like that. What we're doing is we're trying to rationalize this denominator. We have to multiply top and bottom by something so that we get a perfect cube on bottom. And what I will look to do, it's what the book did as well. Go to the lecture and see what I was talking about with it. What I would look to do is just look at your list of perfect cubes. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, etc. 8 can be achieved by doing 4 times 2. So if I put a 2 here and a 2 there, I'm well on my way. Because this becomes, on bottom, the cube root of 8. And the cube root of 8 is 2. So that's what we're dealing with in our bottom, rationalizing our denominator. Cube root 5 times cube root 2 is cube root 10. So we're just going to be left with cube root 10 all over 2. It's still an irrational number. We couldn't change that. But at least it's now a rationalized number. Rationalized denominator. Number 24. More of the same. We have cube root, or fourth root of 4. Which we already saw that that's 2 root 2, but I don't think we're playing with this that way. We have the fourth root of 4 over fourth root of 27. You know, maybe we could play with it that way, but I don't think it's going to be helpful if we do. Anyway, we're going to try and rationalize this one here as well. We got to multiply 27 by something so large that we're going to come up with what we need. Perfect fourth root values, we can think of our 16. 3 to the fourth is 81. 27 can multiply by 3 to get 81. So let's rationalize this. 27 times 3 is 81, and fourth root of 81 is 3. So we got to multiply top and bottom by this to rationalize in its true form. So on the bottom, fourth root of 81. On top, fourth root of 12. Now, fourth root of 81 is 3, and you have fourth root of 12 over 3. Now, once again, when it comes to simplification, we have to ask ourselves whether there's something we can simplify more on top. And I'd say probably not. As far as perfect fourth value, 16 would be a number we could get from there. But we're going to leave it like that. We're going to leave it like that. When we did the one with the 4, the difference was this wasn't a product of two numbers. Because now this is 4 times 3 in this case, which is 2 squared times 3. But that 3 would be in its own fourth root. So we're going to leave it like that. Number 25. Number 25, we have square root of 3/8. Whoops. Okay. This is one where you want to split it on top and bottom like this. Now, we have two different ways to do this. They both get the same answer. Let me show you both and see which one you prefer on these cases. I probably will prefer the second way. We can rationalize the denominator now by multiplying top and bottom by root 8. Hopefully you're pretty good on your square root bits. Multiply by itself there. You'll get a perfect square guaranteed instead of trying to be clever with it. Although we can talk about cleverness as well, and that's where I'm going to get to the second part. So here we're going to get root 24 over root 64, or 8. And now you got to simplify the top because root 24 is root 4 times root 6, or 2 root 6. And 2 root 6 over 8 gives you 1 root 6 over 4. So root 6 over 4 is the final answer. So there's one method. Second method, taking that same root 3 over root 8. Root 8 can simplify. It can't rationalize, but it can simplify. It's root 4 times root 2, which is 2 root 2. So when I rationalize the denominator here, I can multiply top and bottom. Instead of by root 8, I can just do times root 2 straight up because this 2 is not irrational. I don't need to do anything with that. I just need to do something with this part. And that gives you root 6 over 2 times 2, which is root 6 over 4. So you still get the same answer. The clever part I was talking about is how we have to do it with cube roots and fourth roots and stuff. I could have multiplied root 8 by root 2 straight up because you're like, well, 16 is a perfect square, so I can make it 4 squared. So if I multiply by root 2 right now, okay, but you just have to know that that's what you're doing with it. Most of the time when we rationalize, we just straight up multiply by the thing that's there, square root of it. But if you simplify it first, you can work off that. Now, if you prefer this, it's up to you. You still had to simplify the top. You still had to reduce the fractions. Here, I simplified the bottom first, wrote all that I needed to there, and then I was good. Number 26, we have cube root of 7/4, which can be rewritten as cube root of 7 over cube root of 4. Now listen, you might say, well, wait, why can't we just do cube root of 4 over cube root of 4? Because this doesn't equal 4. It's not the same as square root of 4 over square root of 4. Cube root of 4 over cube root of 4 is cube root of 16. 16 is not a perfect cube. So you can't just do that. You can multiply. If I change color here, remember, we have to come up with a perfect cube. This is what I kind of said in the lecture portion of it. I said that 4 is just 4 to the first power. What if I turn it into 4 to the third power by multiplying by, 4 squared, like that? Because what's going to happen here is, on bottom, this would become cube root of 4 cubed, which is just 4, and that's great. What we're actually really multiplying by here is 16. Now, why are we multiplying by 16? Because it's a perfect cube that can go into there and clean it up. Now, is this the smallest perfect cube? It's not. That's why this isn't necessarily the way to always go about it. So here's one method, multiplying by the thing to erase the perfect cube, just like we did on this top one here, multiplying by root 8, just get rid of the 8. But there will be more to take care of now here, because 7 times 16, well, I don't know, 7 times 16, it's 112. And you have cube root of 112, but unfortunately for you, 112 is a perfect cube of 8 inside of it. It's 8 and, I got to figure it out. I just know that it's 8. It's 8 and 13. So that becomes 2 times cube root of 13 over 4, and 2/4 is 1/2. So it's cube root of 13 over 2. So now we go back to the other way that we probably would have done this problem, which is just taking this guy right here, taking that right there, and then multiplying by the smallest perfect cube that we can, multiply by the number to get us the smallest perfect cube that we need. We can multiply by 2 here and here, because 4 could have turned into 2 squared. 4 could have turned into 2 squared, and 2 squared just needs, and 2 squared just needs a 2 to the first power to to get finished there. So it depends on how you're working on this stuff and how you best understand it. But that's what we can do here. That's why we get the cube root of 8. And this is now the cube root of, oh, it's 14, not 13. I apologize. That's a 14. That's a 14. See, it's a good thing we're doing the problem twice. For some reason in my head, 8 times 3 was 32. A lot of my students do that. That's the first time I've ever done that in my life. Problem is I'm talking to you guys while I'm doing it. All right, cube root of 14 over 2 is still the answer that we got there. Which one do you like more? Up to you. I'm going to have to consolidate down to one method pretty soon, as I say, or you can do this or you can do that. And then you decide if you like the other method if I just do one of them. 27, I have cube root of 64 over 49. If only this were a square root, that'd be perfect because these are perfect square values, but they are not perfect cube values. And these don't reduce. So this can simplify to the cube root of 64 over cube root of 49. Now, what I might do here in terms of rationalizing is instead of trying to find a number to multiply this thing with, is 49 might be big enough to have a perfect cube. And it doesn't. It doesn't have a number that's big enough to be a perfect cube. But it is 7 squared. And that's where I want to bear, this is where it bears repeating what I want to say here. I think cube root of 64 can break down. And I'm going to get into that a little bit. But this is 7 squared, which gets down to the idea that I just need to multiply this by another 7. 7 to the first power, right? Because then it'll become 7 on bottom. This will become the cube root of 7 cubed, which is 7, right? So this will break that down. And I think to the smallest extent possible. 7's a prime number, and there's just nothing else I'm going to be able to do with it. Now, that being said, 64. 64 has a perfect cube of 8 inside of it. The cube root of 8 is 2, and there's another cube root of 8. Oh, 64 is a perfect cube. What am I doing? 64 is a perfect cube of 4. Okay. Anyway, let's do that again. That is 4. All right, times cube root of 7. And that's 4 times cube root of 7 like that. So you're done with that. Sorry, I was thinking too much about the simplification rules that I missed my perfect cube when it was there. All right, so that'll be it for number 27. And number 28, they're probably throwing one of those in there for us as well. Maybe 1296 is a perfect cube. Oh, it's a perfect fourth power value. Sorry, it's perfect fourth power. 1296 over 25. Because they often, work things out like you just saw. Let's first write this. It's the fourth root of 1296 over fourth root of 25. And I don't have ways of making this smaller for you without you kind of practicing some things. Maybe you have to use the calculator. If you might notice, powers of 6 always end in 6. Okay, so maybe you always want to try one of those first. 6 squared is 36. 6 cubed is 216. 6 to the fourth is indeed 1296. So best I'm just going to say for you right now, guys, is this number 6. As far as fourth root of 25 goes, I want to work with this in the same light as I did right here. I want to turn this into 5 squared. Now, before I say, let's multiply by another fourth root of 5 squared, keep in mind, this is the fourth root of 5 squared, which is also, remember, 5 to the 4th power, which means 5 to the 1/2 power, which means this is also the square root of 5. So I've simplified that in and of itself into something a little bit better for this. When it comes to our final answer, we're going to want that. It's still not rationalized, but it's simplified. So now we multiply just by root 5 over root 5, and now we get 6 root 5 all over 5. And that's going to be the best, cleanest of the answers that we got. Most simplified, of course. Okay. Let's move on. We have 82 total problems, so we just got more to do. In 29 to 36, write the expression in simplest form. Now, this is where we have to rationalize the denominator, but it doesn't work to just multiply by root 3 over root 3 because we got to distribute here, and that won't rationalize when root 3 multiplies with 1. So instead, we have to multiply by its conjugate. The conjugate, if this is a plus root b, we got to multiply by a minus root b. This is what gets you a difference of 2 squares, a squared minus b squared. And in the case of the bottom, that's a squared minus b squared. And yes, over time, I'm going to write that faster than I did here. 1 times 1 and 1 times negative root 3 happens there. Of course, that just is still 1 minus root 3. But now this is rationalized in the denominator because the denominator is 1 minus 3. And 1 minus 3 is negative 2. So you have 1 minus root 3 over negative 2. Now, you don't want to leave your answer like this. One of the other simplification rules that we tend to do is we don't want negative leading terms in a denominator. If that's your only term, you don't want to leave it like that. This is going to be a little bit different for you to kind of hear, so listen up. You can take the negative 2. See, you can take the negative anywhere in this thing and apply it. It can go in front of the fraction like that. It's kind of weird looking. Or you can take it and distribute into these ones here. Negative 1 plus root 3 over 2. Here's a good answer that I like. I'll box this answer just in case that's what they do. Or you can put this leading term positive like that. You know, make the leading term always positive. Put the root 3 in front. These are good answers right here. I kind of like this one or this one most compared to that. This is a way of having your denominator positive. So I'm always going to go for positive denominators. Part of your simplification rules, really. So get used to having a lot of those. Number 30. Number 30, we have 1 over 2 plus root 5. And now we got to multiply top and bottom by its conjugate. In this case, it's 2 minus root 5. More of the same. This becomes, we distribute the top, that's 2 minus root 5. And on the bottom, we're going to do a squared minus b squared. That's the difference of two squares. That's why we multiplied by its conjugate. Now that becomes 2 minus root 5 over negative 1. And once again, that's a weird way to write that answer. Let's divide these by negative 1. First of all, the 1 doesn't really matter. The negative does, but what does the negative do is it changes your signs. Negative 2 and plus root 5. Is this a good answer for you? I like it. I also like root 5 minus 2. I think I like the first answer more. Negative 2 plus root 5, done with that. But you don't want to just leave it over negative 1. That's silly. That's silly. We're not going to do something like that. That's why simplification is to be had. Number 31, we have 5 over 3 minus root 2. Now, all of these have rationalizing the denominator, so I think after the first 4 of them, I'm really going to get in that bottom half being a really quick done thing. The conjugate of 3 minus root 2 is 3 plus root 2. It always has to be the opposite sign of the second term to get the difference of two squares effect. Now, on the bottom, that becomes 3 squared minus root 2 squared. On the top, you must distribute this 5 into the 3 and the root 2, and you get 15 plus 5 root 2. 9 minus 2 is 7, so you get 15 plus 5 root 2 all over 7. And you're actually done there. Everything's positive. That's all good to go. Let's move these over a little bit. Okay. And nothing can reduce, so you're good. Or simplify. Number 32, we have 11 over 9 minus root 6. Let's multiply by its conjugate on the bottom. 9 plus root 6 over 9 plus root 6. Get our difference of two squares effect of 9 squared minus root 6 squared, which is 81 minus 6. And on top, 11 distributes into these two here. We get 99 plus 11 root 6. 81 minus 6 is 75. And on top we have 99 plus 11 root 6. Now, oopsie. No, come back. Now, 99 and 75 can both divide by 3. 99 over 3 is 33. 75 over 3 is 25. But 11 can't divide by 3. So in general, whenever we write these things, we're not just going to simplify one part of the fraction. And by the way, 99 over 75, it's not like it's an integer value. It's not like it turns into 2. So it's not like we just reduce only one portion and not the other. We got to reduce both at the same time, and they can't. So we're going to leave that as the answer on number 32. Now, number 33, now they turn into both radicals, but I think just as fast we can work these out. 9 over root 3 plus root 7, it doesn't change as far as conjugation. It's still a squared minus b squared when you end up multiplying by its conjugate. So we want to multiply by root 3 minus root 7 on top and bottom. This will, once again, on bottom still turn into a squared minus b squared. It might be even easier for you. It just turns into 3 minus 7. So I'm going to go pretty fast on some of those when it comes to the actual subtraction. This distributes on top like that. And on bottom we get a negative 4. Let me write this actually over here. On bottom we get a negative 4. And on top we have the 9 root 3 over, or minus 9 root 7. Now in this case, once again, this could be an answer, but I'd like to turn this positive, the 4, by turning the top negative. When I turn the top negative, that means this sign changes, and this sign changes. Is this an answer? Sure. Now my preferred answer, because these are both radicals, is I'd like to get this one leading here. This is just a preference. It's one of those, if you wrote it in photomath, this is probably, or if you took a picture of the problem in photomath, this is probably what they'd say. I don't know for sure, but that's my favorite appearance of that problem, personally. Number 34, you have 2. You have 2 over root 8 plus root 7. Its conjugate being root 8 minus root 7. Now, root 8 can simplify to 2 root 2. I think we're going to get to that over time, but for the time being, let's just work on that denominator being, a squared minus b squared. And guys, 8 minus 7 is 1. So this is just 1 on bottom. On top, we have 2 root 8 minus 2 root 7 when distributed. Now, the 1 doesn't matter to us anymore. That means no more fraction. So we'd almost be done with 2 root 8 minus 2 root 7. But the square root of 8, like I said, can simplify. That turns into 2 root 2. And 2 times 2 here is 4. So you get 4 root 2 minus 2 root 7. This would be your final. Number 35. Root 6 is on top. So we have some more radicals to deal with now. Root 6 on top, root 3 minus root 5 on bottom. Let's go for conjugation. Or rationalization with conjugate. Okay, so on bottom will become 3 minus 5. That's negative 2. Keep in mind how I'm doing it that fast now. Difference of 2 squares. Now on top, root 6 times root 3 is root 18. Root 6 times root 5 is root 30. We actually multiply irrationals with irrationals in that way. They merge together. It's a property we're talking about here. Now, 18 has a perfect square of 9 in it. That's root 9 times root 2, which is 3 root 2. So this becomes 3 root 2, and this becomes, well, that's just root 30. There's nothing we can do with that one. And this is still negative 2, but it is still negative 2. I'm going to turn that positive. We'll turn these ones negative on top. You can also do something, whoops, that has to turn negative as well. You can also do something like turn the whole fraction negative. So this is an answer that I'm good with. Okay. Another version of that answer, again, if you want to turn the fraction negative, meaning it's a negative 1 times the entire thing, like that. I'm just making sure that keeping it separate so you can see for sure is how it is. So that or that. I probably just like this one right here, but I don't like my denominators negative. I don't think the math gods do as well. Number 36. We have root 7 over root 10 minus root 2. Let's multiply top and bottom by root 10 plus root 2. And on bottom, we'll get 10 minus 2, which is 8. On top, we have root 70 plus root 14. And I'll be honest, I don't think these have any perfect square values in them at all. I think we leave it like that. 70 is 7 times 10. 10 is 2 times 5. So there's no duplicates of there. 14 is 2 times 7. No duplicates of those primes. We're just done right there. That's as simplified as you can get. So rationalized and all good. Okay, let's go to numbers 37 to 46, where we are going to simplify the expressions. This is ones where we have addition and subtraction. This is where we combine like terms, what they call like radicals. If I say like terms, apologies. They'll be like to me. In this first one, straight up, you got 9 times cube root of 11 plus 3 times cube root of 11. This is like as if it said 9x plus 3x, okay? 9x plus 3x. We know that's 12x. Well, if x is cube root of 11, this would become 12. I'm trying to change my color. 12 times cube root of 11, and that's it. You combine like terms. They can add. That's part of why we do the simplification stuff that we do. And we'll run into a problem like that when we have to, because it allows us to combine things that we otherwise couldn't and compare things that we otherwise couldn't. That's a big part of it. Number 38, we have 8 times 6 root of 5 minus 12 times 6 root of 5. Like terms, 8 minus 12 is negative 4. You get negative 4 times 6 root of 5. I'm done. The book's doing a lot of this common factor thing, but as long as it's a like terms thing, I hope you understand why combining like terms is what it is in general, and we're doing the same thing here. This should go without saying that it's worth checking because they say simplify. Can I take the cube root of 11? Can I simplify it, or the 6 root of 5? No, but you have to look into those ones and make sure that you can before you finish up your problem. All right, 3 times 11 to the 1/4 plus 9 times 11 to the 1/4. First things first, they're fine with having fractional exponents in your final answer if need be. Next things within this particular problem, PEMDAS is in order. No, I can't do 3 times 11. No, I can't do 9 times 11. They're both being raised to the 1/4 power, exponents before multiplication. However, because now these are like terms, this and this are the same, we can add the 3 and the 9, and 3 plus 9 is 12. So you get 12 times 11 to the 1/4. Can I do anything with that? No. I'm just going to leave it like that. You could turn it into 12 times the 4th root of 11, and if that helps you better understand why we can't multiply those things together, just like we couldn't before. 12 times cube root 11, can't multiply it. 12 times 4th root 11, can't multiply them. So if that helps you better understand it, even though I said that the book tends to write those ones as fraction answers and keep it like that, yeah, whatever. Number 40, you have 13 times 8 to the 3/4 power minus 4 times 8 to the 3/4 power. I mean, so far, every problem is just as simple as combining like terms here. In this case, this will be 9 times 8 to the 3/4 power. I'm a little more inclined to look at working in something on that 8 to the 3/4 power and simplifying it. I'd like to. This may be the answer that the book would go for just because that can't simplify to a perfect value, but I do want to work with it. 8 to the 3/4 power is the 4th root of 8 cubed. Now, 8 cubed, keep in mind, is also, well, 8 is also 2 cubed. So now I can take 2 cubed, and the 4th root of that, and that becomes 2 to the 9th and the 4th root of that. I'm probably speaking beyond what we're going to do here, but 2 to the 9/4. I can divide out 2 of those. 4 can go into 9 twice. So that becomes 2 squared on the outside. And on the inside, I still have another 2 inside that 4th root. And 2 squared is 4. So we can do 9 times 2 squared, or 9 times 4, which is 36. So this can also be written as 36 times the 4th root of 2, or in the fraction form, 36 times 2 to the 1/4 power. Now, do they want those answers? I don't know. I feel like this is just them practicing just that other little part and combining like terms. I'm sure they're going to leave the other one just fine. A photomath answer would do that, I'm sure. I'd love to go into photomath and figure out whether or not that's the case, but I'm sure the photomath answer would say something like that. Anyway, I know this is a little more work than we're actually at just right now. We'll do this more when they talk about ones with variables, I think. But those are other versions of the answers I like to get into. Depends on what kind of teacher you're working with. Number 41. Now, number 41 is the first instance of terms that don't appear alike yet because the radicals aren't the same. So we have 5 root 12 minus 19 root 3. But unless they expect you to not do anything with the problem and say, well, I can't do anything and I'm done, then expect you got to do something. In which case, root 12 has a perfect square factor and it can be simplified. It can turn into 2 root 3, as it's root 4 times root 3. And 5 times 2 is 10. So you end up getting 10 root 3 minus 19 root 3. You see 5 root 12 and 10 root 3 are equivalent to each other, but now I can actually combine these because they have the like terms of root 3. 10 minus 19 is negative 9. So you get negative 9 root 3, and then you're done. And then you're done on 41. Number 42, 27 root 6 plus 7 root 150, and it's one of those things again that you're looking for trouble. Trouble is afoot. I can't just leave this like this. 150, that's 15 times 10, but that doesn't get you perfect square values. What you're really looking for is, because 6 can't break down more, honestly, you're looking for something that can be something root 6. Automatically you're saying, it's got to be something root 6, right? 150 divided by 6 is 25. All right, 25 is, square root of 25 is 5, so it becomes that. So if you were hunting around for what it is, 25 is the largest perfect square you can pull out. Anyway, 7 times 5 is 35. So you get 35 root 6, and now we do have those like terms that can combine. 27 plus 35 is 62. So you get 62 root 6. We all good? We're there. And we're more than halfway through all our problems, by the way, because we're going up to 82. But maybe the hard stuff has just begun. I don't know. Number 43. We have fifth root of 224 plus 3 times the fifth root of 7. And it's one of those things that I'm looking at this and I'm saying, I can probably turn it into something times the fifth root of 7 here. I got to figure out what it is. I don't actually know. I have a good guess of one, which is let's divide 224 by 7. You could do that. But also, you're trying to find a perfect fifth power. I'm guessing it's 32, because otherwise you're looking at, 64 is, 64 won't work. But, 64 is not a fifth power. 3 to the fifth is 243. It must be 32. It must be 32. Is 224 divided by 7 32? Yeah, it seems like it is. So what's the fifth root of 32? It's 2. Anyway, so like I'm saying, if you're without a calculator, assume that the problem is trying to get you to go somewhere with it and say, where are you taking me? If you don't know the number to begin with to factor out, and they can help lead you a little bit. 2 plus 3 is 5. You get 5 times the fifth root of 7. We good. Number 44. 44. We have 7 times the cube root of 2 minus the cube root of 128. Once again, it would be nice if this was a cube root of 2, wouldn't it? I think that'd be pretty splendid. So, whoopsie. So let's divide 128 by 2, because that way then the cube root of 2 is part of the factorization. Then you're left with 64. The cube root of 64 is 4. They're not going to trick me this time. I know I can take its cube root. So there we go, right? That's fact. So again, you can go one or the other. When it comes to problems like these, ask yourself, now, why would they want us to do this? It's not a guarantee, but that's something to look for, and that would work. Otherwise, just find the largest perfect cube. It's 64. And then we get that 7 minus 4 is 3. You get 3 times the cube root of 2. And I think I've overspoken on that concept, and I shan't no more unless I feel like it's a necessity. Number 45, we have 5 times 20, we have 5 times 24 to the 1/3 power minus 4 times 3 to the 1/3 power. Need not remind you on order of operations, I can't do 5 times 24 or 4 times 3. Honestly, what I would want to do with these, and I most prefer having numbers written this way almost always. You've seen exceptions to it so far, but I'd rather rewrite this as the cube root of 24, and this is the cube root of 3. At least they're both cube roots, but they're not the same radicand. So we probably have to turn that 24 into a 3 somewhere. 8 is a perfect cube. That's a factor of 24. The cube root of 8 is 2, and 8 times 3 is 24, so it becomes that. And then 4 times the cube root of 3. So we're going to leave it in this radical form. I'll write my final answer with a fraction involved in case like the book or whatever your teacher would do that. And you're saying, hey, how did we write this? This is where we're beginning it, though. Getting in the style to get us an understanding of what we were dealing with, right? We're not taking a third of 24. This doesn't become 8, and this doesn't become 1. It's nothing like that. Anyway, 10 minus 4 is 6. You get 6 times the cube root of 3. There's an answer. Of course, you can also say 6 times 3 to the 1/3 power, like that. Either or, don't know which one you prefer, but they both work themselves out in that way. Okay. And number 46, last one in this set. Five to the 1/4 power. Ooh, that looks ugly. Plus 6 times 405 to the 1/4 power. That's the 4th root of 5 plus 6 times the 4th root of 405. Let's just divide 405 by 5 right now and hope that we strike dumb luck here. Not really dumb luck, but just, hey, that's what the book would have wanted. 405 divided by 5. Let me just write this on the side just so you know what I'm talking about. That's 81, and 81 is indeed a perfect 4th root guy. 4th root of 81 is 3, so this can become 6 times 3 times the 4th root of 5, right? That's what we're dealing with there. Just right over here. This is 4th root of 5 times, or plus, 18 times the 4th root of 5. So, like terms there. Remember, this 4th root of 5 means 1 times the 4th root of 5. So we have to do 1 plus 18. So we get 19. 19 times the 4th root of 5 is a final answer. One with the fractional exponent that we had originally would be 19 times 5 to the 1/4 power like that. I personally prefer the one on the left, but have it your way. BK, baby. All right, error analysis. This might not be the only one, but this is the only one on this page. So number 47, describe and correct the error in simplifying the expression. So 47. So they have 3 times cube root of 12 plus 5 times cube root of 12. They end up kind of doing a factored version of this thing where they factor the cube root. Oh, no, they wrote a 24. Oh, no. Oh, no. No. That should still be a 12. This should still be a 12. Now, you'll notice there that they're doing some simplification stuff after this. None of this stuff matters to me now because this should still be a 12, not a 24. If we want to do some factorization on it because it needs it, great, but it shouldn't need it on that one. So their problem is when factoring, which I don't write it as factorization, but when factoring cube root of 12, I don't have a better way of writing it right now, out of 3 and 5, they doubled up the number. I guess they were kind of adding it. They doubled up the number to 24. They shouldn't not do that. They shouldn't have done that. They shouldn't have done this. Hey, shouldn't have is a perfect double contraction. And you are a they. Come on now. They shouldn't have done that. All right, I'm going to write it like that. So what can they do? As simple as you guys know best. 3 times cube root of 12 plus 5 times cube root of 12. Treat them like x's, combine like terms. They are alike. And this becomes 8 times cube root of 12. And honestly, I'd be done right there. 12 isn't a perfect cube. 12 doesn't have perfect cube factors. The smallest perfect cube is 8. So we'll leave it. All right. That was the only error analysis. Interesting. There were a lot of things we could have talked about from any of the 46 problems or whatever before. There are a lot of different things we could have talked about and said, well, here's where people make mistakes. And I'm surprised. Oh, there's some more below. Okay. Even though it's for different kinds of questions. All right, number 48, multiple representations. Which radical expressions are like radicals? Ooh, this is interesting because we still have to do kind of every which problem on here. So for A, we have 5 to the 2/9 raised to the 3/2. Let's start working that out a little bit. Remember, that means you're multiplying 2/9 with 3/2. And 2 over 2 is 1. 3 over 9 is 1/3. So you get 5 to the 1/3 power. So we're probably looking for something that goes to that, or cube root of 5, of course. So either of these we're looking for as a representation that matches with A, perhaps. Maybe none match with A. Maybe A stands alone, it's on its own. B, we have 5 to the 3rd over the cube root of 5, all raised to the 8th power. If I were to do something with this personally, this is probably where I'd rewrite this in fraction form, because my goal is not to evaluate this number, but it's to work it with other numbers, like I would with variables. So that's 5 cubed over 5 to the 8/3 power. That's the rewrite. So that means I can subtract these exponents, 3 minus 8/3. But now I need a common denominator. 3 is also 9/3. So 5 to the 9/3 minus 8/3, and 9/3 minus 8/3 is 1/3. So you get 5 to the 1/3 power. We know that as the cube root of 5, so I'm just going to go ahead and say that those do align. So for now, A and B are golden. I don't really know where to write this, I guess at the top. A and B are the same. Okay, part C. And I'm reaching the bottom of the page. Boo hiss. Part C, we have cube root of 625. Now, 625 can break up into 125 is 5 cubed, and you can divide 125 by 625 and you get 5. So you get cube root of 125 times cube root of 5. And cube root of 125 is 5, like I said, so that's 5 times the cube root of 5. Now, you could be done here. If you want different versions of this, just so we understand whether it's the same as this or not, clearly it's not the same because the cube root of 5 is not the same as the 5 times the cube root of 5. But if you do want to see other representations of this, this is also 5 to the 1st times 5 to the 1/3 power, which 1 plus 1/3 is 1 1/3 or 4/3. So it's also 5 to the 4/3 power. So C is a different kind of answer than A and B. C may match up with a different kind of answer, but I'm giving different versions of what we have here and what we're writing, just in case we fall into one of those. So here's an answer, there's an answer for C. Part D, we have some big stuff. Cube root of 5145 minus cube root of 875. And honestly, I'm going to have to work on these a little bit. Now, 875, I'm seeing in my head that 125, we can still kind of work out with it being a perfect cube and all. 125 times 7 is 875. So this one becomes, just on this one alone, cube root of 5 is, cube root of 125 is 5. So 5 times the cube root of 7. So my goal and understanding is I'm going to try and probably divide this one by 7 and see what comes out and see if it's a perfect cube. I'm actually going to use the calculator for that one. Let's check it out. 5145 divided by 7. Normally I wouldn't do that, but I want to see. That's 735. So the only problem with that is 735, to my knowledge, is not a perfect cube of anything. Now, that's not to say these can always simplify. That was just my guess and that it could. Let me make sure that 875 divided by 7 is 125. It is. So, yeah, I don't know as far as perfect cube things, right? That gets a little massive. 5,145 divided by 7 is indeed 735. So let me, you know what? Let's divide it by 125. Let's do that instead. 5145 divided by 125. Oh, that doesn't work out. So this breaks up into, and this doesn't help me yet. 730 cube root of 735 times cube root of 7. And then minus that. My basic understanding of that is unless 735 is a perfect cube, which it's not, I don't really know what I can do with that. So I'm just going to treat D as kind of its own thing unless I find something else that can, because listen, here's the thing. That's not going to have a cube root of 5 status on it anyway. So I think this is just a different thing in and of itself. I don't think it's working. I don't think it's working in that way. Part E. Part E is, sorry, we're going to kind of run out of paper space down here. Cube root of 5 plus 3 times cube root of 5. Straight up, that's 1 times cube root of 5 plus 3 times cube root of 5. That's 4 times cube root of 5. 4 times cube root of 5 is here. We did have 5 times cube root of 5 over here. Keep in mind, they're not the same, but we did have that. So I'm just going to box this one, by the way. So there's that. It's also different from all our other answers. And part F, we have 7 times 4th root of 80 minus 2 times 4th root of 405. Let's start on that 4th root of 80. 16 is a perfect 4th power value of 2. So 7 times 2 times, and 80 divided by 16 is 5, so you'll get that. Minus, well, you can divide this by 5 and get 81. We've seen that, and the 4th root of 81 is 3, so I can do 2 times 3 times the 4th root of 5 as well. So this becomes 14 times 4th root of 5 minus 6 times 4th root of 5, which is 7 times 4th root of 5, like that. So these are all different kinds of answers there. It's nice. Oh, sorry, 7. 8. These are all different kinds of answers there. They're cool. These all simplify. D didn't simplify to my liking, but it still did simplify in and of itself, or whatever. It didn't simplify to my liking, but it didn't match another answer, and it won't match another answer. It looks like only A and B were the only true ones to actually match up as something. I expected like 4 of them to match up, or other ones to match up with other ones, and it seems like these were the only ones that actually did something with each other. So just A and B work out in that sense, unless there's something that I'm totally missing on these problems because they said which ones are like radicals. Let me just double check everything and see if I'm missing something on. Oh, they just said like radicals. They didn't say similar expressions. They said which of the following are like radicals. Okay, I take back what I stated. Now, these are the exact same answer on A and B. These are the exact same answer on A and B. But, or whatever. But these are all cube root of 5. C has a cube root of 5. D does not. E has a cube root of 5. F has a 4th root of 5. So I'm going to change it from A and B to A, B, C, and E. They didn't say which of the following expressions are equivalent. They said which of the following are like radicals. You know, as far as could I combine them when I add them? These are the ones that could combine when I add them. So I'm going to say A, B, C, and E. Okay. Okay. Let's go to 49 to 54, where we are going to simplify the expression. Now, I spent a little bit of time in the lecture portion talking about what to do. The problem is I tried to tie in what I do with what the book does, and I'm just going to do with what I do now. So, and there are ways I'm going to do it faster over time. I just want to make sure that I get some inklings of it here. They don't say assume the variable's positive, so we're not going to assume that. Okay, so first and foremost, I'd like to treat these ones separately, numbers with numbers, variables with variables, that kind of thing like that. Let's start with this one. The fourth root of 81 is indeed just 3. The fourth root of y to the 8th, if it helps you write it out first, you can rewrite it to y to the 8 over 4 power, which is a way of saying that, yes, we divide this exponent by that exponent. That means this is 3 times y squared. And that's it. Number 50. On number 50, we have the cube root of 64 times r cubed times t to the 6th power. They're all within that cube root. If you want to treat them separately, you can write them separately if that helps you. It doesn't help me per se, but it helps me help you with what we're talking about. Now, the cube root of 64 is just 4. Perfect cube. Cube root of r cubed, think about what we just did right here. We're going to divide 3 by 3 and we get 1. So that's times r to the first power. And same thing here. T to the 6 over 3 power is t to the second power. So this becomes 4rt squared. There's no absolute value we have to do with this r because we're taking the cube root. We're doing odd roots and odd powers like that. It's only with even roots that we're going to have to do that with when it turns into a raised to a first power or odd power kind of deal. And that's not the case right there. Number 51. We have the fifth root. We have the fifth root of m to the 10th over n to the 5th. Once again, if you need to treat them separately, there's the fifth root of m to the 10th over the fifth root of n to the 5th, but they're still dividing. 10 divided by 5 is 2, you get m squared. 5 divided by 5 is 1, you just get n. You have m squared over n. So hopefully that makes sense in division and what we're doing, but if you need the rewrite into rational exponential form, that can help you get there. Number 52. And remember, it's just with exponents that they divide, not the base values of numbers. Number 52, let's see if we can do this one without use of splitting it up. We got k to the 16th over 16 times z to the 4th. Now, the k, we divide these exponents by 4 here and here. So 16 divided by 4 is 4. You get k to the 4th power. The fourth root of 16 is not 4. It is 2. 2 to the 4th is 16. So you got to be careful there. We divide this by 4, but we take the fourth root here. This is a base value. We're taking the fourth root of that. So that becomes 2 here. 4 divided by 4 is 1 for z, so we get a z down there. The difference here with the z is, because it's now z to the first, a negative number raised to the first would be a negative number. A positive number raised to the first would be a positive number. But a negative number raised to an even power would turn positive. So we have to make sure this stays positive. We got to write absolute value of z down there. It's rationalized. We're good. It's a perfect, whatever value. But we have to put an absolute value around that. We're not assuming your variables are positive here. Number 53. Number 53, I want to do a step before I apply the radical for at least the h's, but we'll do it all as one. G to the 6th, h over h to the 7th. What you're going to see me do a lot more with these when it comes to division. Depends on how often we do the problems. But this is h to the first. Let's get rid of that 1 as we're kind of subtracting here. And let's remove an h from down here and just get 6 left. I know it's the same thing as h. So h over h to the 7th is h to the first over h to the 7th is 1 minus 7, which is h to the negative 6, which is 1 over h to the 6th. But you can see I'm skipping all those steps. I'm removing an h from top. It's gone. I'm removing an h from bottom, and it's still on the bottom, but there are 6 of them. So it's still positive. We're still good there. So now we have the 6th root of g to the 6th over h to the 6th, which means both of these exponents get to divide by 6, and you get g over h. Now, because they're both to the first power, if they were negative, we got to turn them back positive in this way, this over that, or we can have it as one big absolute value of g over h. Nothing wrong with having one big absolute value. I suppose, it's as far as rationalization or not, that's not an issue. I'm just saying, I suppose with that, we're turning it positive as a whole anyway, so we can treat it just with one whole one, I imagine. There's nothing wrong with that. Let's do is one big absolute value, all good. Number 54. We have the 8th root of n to the 18th times p to the 7th over n to the 2nd times p to the negative 1st. A couple things I can do here. I mentioned this earlier. I like to turn negative exponents positive whenever we have a fraction immediately. That way we don't have any issues. This turns into positive p to the 1st, but it's in the numerator. And over on this guy right here, 18, n to the 18th over n squared. Let's take out both n squareds from here, and let's take out 2 of them from up here. So now you're left with 16 of them. So now this thing looks instead like the 8th root of n to the 16th times p to the 8th, because 7 plus 1 gives you the 8 there. And both of these will be dividing by 8, and both of them can divide by 8. So you get n squared times p to the 1st. Now, as far as absolute values go, p is going to need an absolute value, because what would have been a negative number needs to turn positive when it does. N does not need the absolute value, because squaring a negative number will still turn it positive, just like raising to the 16th power would have turned it positive. So n squared times the absolute value of p is your final result on that. Okay, error analysis on number 55. Describe and correct the error in simplifying the expression. We have some stuff here. Now, they might write it differently, but let's just see if we can still work out the work. They are splitting up this thing as 6th root on top and bottom separately there. All's good with that. 6th root, well, we'll talk about that in a second. 64 is 2 to the 6th power, so the 6th root of 64 is indeed 2. There's nothing wrong with that. The 12 divides by 6 and you get 2. Let's just kind of go off the whole answer there. And 6 divided by 6 is 1 for g, so you get a g. So what's the problem? The problem is that g is not wrapped in an absolute value. So what we're going to need here is, and just that's the last part, everything is correct. Oh, I got to write a 55 here in a second. Everything is correct except the g in the denominator needs an absolute value function wrapped around it. This is because if g was negative, the result of the simplified expression would no longer be equivalent to the original expression. And I want to remind you about that. See, if g is negative in the original expression, when you raise it to the even power, it turns positive. So this, no matter what I plug in for h and g and all that stuff, this is always going to be a positive result. If I plug in that same negative g down here, suddenly it's a negative result, right? What if I plug in negative 2 for g and 1 for h? This becomes 2 over negative 2, which is negative 1, and apparently this would become 2, if you do it, all of it, 2 over 2, which is positive 1. That's not equivalent. It would be equivalent if you put an absolute value around it. So what I'll do instead with this thing here, and I would really just do it in one step because we've been treating it like that lately. 6 root of 64 is 2. 6 root of h to the 12th. 12 divided by 6 is 2. So h squared. And 6 divided by 6 is 1, so you're left with g. But because it's g to the first power, we're going to have to wrap it in absolute values. Make sure we treat those negative guys there. So it's just like that, straight up. Now, h squared, again, doesn't need it because squaring a negative number will still turn it positive, just like to the even root here. Okay, number 56, open-ended. Write 2 variable expressions involving radicals, one that needs absolute value in simplifying, and one that does not need absolute value. Justify your answers. I wonder if justification is with substitution of numbers. Maybe we should actually show it here. So on one of them, we can do something like square root of, let's do 9x squared y to the 4th. Okay, so this one needs it. I need it. This is 3 times absolute value of x times y squared. This is because, once again, this x went from squared to no longer raised to an even power. Now, one that would not need it would be something like the cube root of 81 x to the 6th, y to the 9th. Now, this would become, well, let's actually do this. Let's just do x to the 3rd and kind of do the same stuff. This is because now here, oh, not 81, not 81. Let's do 27. So this becomes 3 times x times y cubed. So again, this one doesn't need it for a couple reasons. Well, actually, this doesn't need it for one reason. We're taking a cube root, not an odd root, not an even root. The y didn't need it here because it's still being squared. but this one needs it here because when you plug something into it, it's going to have to stay positive. Let me give you the example with this one and how it works out here. So let's say that x equals, and actually here, let's do this. Let's turn y into the 6th power so it's like the same looking answer as this one. So y to the 6th power, 6 divided by 3 is 2. So two different forms of the same answer, right? So for these questions, let's do x equals, and I want x to be negative, that's the whole point. Let's make both of them negative. X equals -3 and y equals -2. Okay. So when x equals -3 and y equals -2, let's take the square root of 9 times -3 squared times -2 to the 4th. This would become the square root of 9 times 9, right? -3 squared is 9, -2 to the 4th is 16. Now, to help you out here, we can separate these. This would just become 3 times 3 times 4, which is 36. Now, when I look at this guy right here, 3 times absolute value of x times y squared, 3 times absolute value of -3 times -2 squared would become 3 times 3. Absolute value of -3 is 3 times -2 squared is 4, and you get that 36. So these are the same, and that checks out how we want to. Now, if I didn't put that for this one here, let's say the same x is -3, y is -2. Now we have 3 times -3 times -2 squared. 3 times -3 is -9 times 4, and that gets you -36. That is not the same. That is not the same as this other one that's right there. Whereas if I do it here, I get the -36 like I wanted to. This is 27 times -3 cubed times -2 to the 6th, which is, cube root of 27 times -27 times positive 64, and that becomes cube root of 27 is 3, cube root of -27 is -3, and cube root of 64 is 4, and that becomes, once again, this guy, -36, so that's equivalent. I know I wrote in kind of rough spots. This is just my justification of it. I already did the open-ended portion. But it just goes to show you don't want an absolute value here. It's not that you don't need one. You don't want one here. You do want one here, absolutely guaranteed. Okay, in exercises 57 to 64, write the expression in simplest form. Assume all variables are positive. That means here we no longer need to talk about absolute value stuff. Everything's positive to begin with. No plugging in -3s or anything like that as a whole. But there's probably more to be had in this when it comes to simplifying. That's going to be trickier, tougher, and I already see it right now. Now, the book might say it differently than this. Your teacher might say it differently than this. This is how I go about these problems. First of all, we can treat these separately as need be. Numbers with numbers, A's with A's, B's with B's, C's with C's. Nothing changes as far as what we were doing from before. Keep in mind, taking the square root of 81 is 9. Taking the square root of these, I'm going to write it like this to begin with and see what works best for us as a whole. I'm going to write it like this to begin with just to remind you of what's going on. This is indeed division on the exponents. Now, as far as B, 12 divided by 2 is 6. That's great. As far as A, 7 divided by 2. So 3.5, 3.5. We don't do that, though. We got to think more long division. And we've done long division because we did the previous chapter, although it wasn't with numbers. 2 goes into 7 3 times. 2 times 3 is 6. 7 minus 6 is 1. That's a remainder. This is the quotient. This is the remainder. The quotient is the number that can pull out. The reason is because a to the 7/12 isn't just 3.5 or 3 remainder 1. It's a to the 6 halves times a to the 1 half. 6 halves is 3. 9a cubed, and here's a to the 1 half. That's 3 plus 1 half. That's where that comes from. Now, what I'm going to do with this is slightly different. I'm not going to do this way every time. 9 halves is the same thing. That is 8 halves. Actually, this probably is what the book does to begin with. Times 1 half. Whoopsie, I'll do it right here. 8 halves times c to the 1 half, which is 4 times 1 half. Now, the 1 halves are radical values. Those are square roots. Those stay inside square roots. Anything that's a whole number comes outside. This is 9a cubed times b to the 6th times c to the 4th, with times the square root of a times c. These two did not pull out of here. These, like this 7 divided by 2 is 3 with the remainder of 1. Here's 3 with the remainder of 1. The quotient, here's how I'm going to do it here on out. The quotient comes on the outside in the division. The remainder stays in the inside. A to the first is not a perfect square value. You couldn't pull it out of there, so it doesn't come out of it. I don't know if that's the one the book did with fractions. I'm going to do a secondary one on this next question. That's the final answer, by the way. I'll do a secondary one on this next question in the same light, but this time not with fraction exponents. I'll keep them as radicals and talk about division in the same way, though, and I'll split them up inside the radical. That might be what the book does. So number 58, we'll do cube root of 125, r to the 4th, s to the 9th, times t to the 7th. As far as treating them in separate terms and stuff like that, I mean, we can do that. That's cube root of 125. I probably won't be doing it much here on out. Times cube root of, now r to the 4th. R to the 4th can be rewritten as r cubed times r to the 1st. Now, why would I ever do that? Because 4 divided by 3 is 1 with the remainder of 1. But what we're going to do is split this up in such a way that we can take the 3 divided by the 3 right here. That's what we're doing with that. Now, s to the 9th, we'll just split it up for now. Cube root of s to the 9th. 9 can divide by 3. And 7 cannot divide by 3, so you split up into a number that can divide by 3. 6 can divide by 3, and the 1 that remains cannot. Cube root of 125 is 5. Cube root of r cubed, 3 divided by 3 is 1. You just have r. Even if you could do absolute values on these things, even if the, if this was squared, even if they were absolute value based, we're assuming all variables are positive, so we're not doing any absolute values. Anyway, times the cube root of r. This one remains inside, it doesn't change. 9 divided by 3 is 3, so that comes outside, and 6 divided by 3 is 2. As that one comes outside, this one remains inside the cube root. So we write everything on the outside stays on the outside. 5, r, s cubed, and t squared. On the inside of that single cube root will be the following, r and t. So hopefully I'm getting something out of that with you guys. I am planning on going faster with those as a whole. As far as the quotient is what pulls out, the remainder is what stays inside. I can't take the cube root of r to a power that's less than 3. Even if it said r squared, I still can't take its cube root. It stays inside. It's a remainder. It's a remainder. Anything else that pulled out did come out in its simplified way. The exponent divided by 3. I took the cube root of 125. It's no different than these numbers here. Maybe that's why they do those the way that they do in the book, because they treat numbers that way. But I like to treat numbers as numbers, if you know what I mean. All right, number 59. We have the 5th root of 160 m to the 6th over n to the 7th. Now, we have a lot to say on this one, don't we? Let's treat these separately because we have a lot to say. A lot to say. In fact, I wonder to what extent they actually want this thing. I'm curious whether they'd want a denominator rationalized or not, because this thing, guys, is going to be an irrational denominator. This could actually be a hoot. I'm going to go ahead and say rational denominators is what we're going to have to go for. First of all, 160 is not a perfect 5th power value. 32 is, and 32 can divide out of 160. The 5th root of 32 is 2, so this becomes 2 times the 5th root of, it's 32 times 5. So 32 times 5 is 160, so 2 times 5th root of 5 for that guy. Second one, m to the 6th. 6 divided by 5 is 1 with a remainder of 1. Oops, don't put equals. It's 1 with a remainder of 1. So this 1 is the quotient with a remainder of 1. When I say 1, I'm talking about these invisible exponents. Boom, boom. 1 with a remainder of 1 is inside, like that. The last one for n's, 7 divided by 5 is 1 with a remainder of 2. 7 divided by 5 is 1 with a remainder of 2. Like that. So as a whole, what we now presently have is, on top we have 2m times the 5th root of 5m. And on bottom, we have n times the 5th root of n squared. The only reason I didn't combine the top with the bottom right now is because we're actually not done. That bottom actually needs to be rationalized. I need to go ahead and come up with the thing that rationalizes the denominator as a whole. So I actually need more room on this thing like this. I need to multiply the bottom by something that I can take the 5th root of n with. And this is where, that exponent talk we talked about with numbers actually works out here. I need to turn this 2 into a 5. I need to be able to divide 5 by 5 to work this out. So in order to do that, I need to multiply n squared by n cubed. Remember, the exponents will end up adding in this case. So n cubed needs to multiply on top and bottom, and then we'll end up actually having a rational denominator. Because now we have, on bottom, we still have the n, and this is going to be multiplying by the fifth root of n to the fifth, right? 5 can divide by 5. We're going to deal with that in just a second. And now on top, we need to multiply these two fifth roots together. They can actually fuse together. So this is 2m times the fifth root of 5m n cubed. And again, fifth root of n to the fifth is n, and n times n is n squared. So you end up getting 2m times the fifth root of 5m n cubed over n squared. And that's a rationalized denominator answer, right? Those are the kinds of ones that we're trying to look for as a whole when we are finished, when all said and done. Number 60. Probably more of the same to do. Let's take a look. Well, actually, this one might clean up a little bit more than you think. Number 60 doesn't look like just a direct copy of number 59. We have the fourth root of 405x cubed y cubed divided by 5 times x to the negative first times y. This one actually is a little bit helpful here. First of all, you can do the numbers with numbers thing like that. I think we can all treat this within the same fourth root if we so prefer. So as far as fourth root stuff goes here, 405 divided by 5 is 81. We've seen that actually a lot now. If I bring up this x to the negative first and turn it into x, this is x to the first times x cubed, which becomes x to the fourth. That's nice. And y to the third divided by y, we remove this y and remove a y from here, we get y squared. So now we have the fourth root of 81 times x to the fourth times y squared. Fourth root of 81 is 3. The fourth root of x to the fourth is x. Remember, variables are positive, so no absolute value. And now y squared can't come out of that 4, so we'd leave it inside. But you have to remember here one more time, we've seen this before. I don't want to write it like that because we're dividing 2 by 4. We are dividing 2 by 4. And if you need to write it in rational exponential form to work that out first, we can. This becomes y to the 2/4 power, which is y to the 1/2 power. You want to reduce the fraction, which means your radical wants to be simplified. This isn't the fourth root of y squared, it's the square root of y to the first. So 3x times the square root of y is your final answer for that one. Now, the one thing about this problem that you'd have to be very careful with as an overall is that this initial y that I canceled out, they said assume all variables are positive, so I'm going to assume that. But you just got to make sure that y isn't 0. We can't be dividing by 0. So normally I'd be saying something like that. In this case, I think I'm good in just saying that assume all variables are positive anyway. So we are good. Because you can't cancel out a 0. You can't cancel out a 0. All right, number 61. We have the cube root of w. I like these problems as far as like the old books that we had for what we taught. Oh, this problem's interesting. That we taught didn't have great problems in this variety, so I had to be inventive and create some of my own. I'll attach some more problems of my own if you'd like. They're probably not as clever as these ones. They definitely don't have a lot as many radicals as these ones, but just simplifying rules. You might want to practice some more. It's up to you. Okay, this one's a little bit interesting just because one is a cube root and these have square roots right here. This is where I'm probably going to work more in the fraction realm where I need to. But let's first begin with what we can simplify and where. The cube root of w can't change right now as it stands. We're just going to leave that. This is the square root of w to the fifth. Don't forget that that's a second root. So is this obviously right here. But 5 is dividing by 2. 5 divided by 2 is 2 with a remainder of 1. Okay? So that's the simplification there. The square root of 25 is 5. The square root of w to the 16th, 16 divided by 2 is 8. So you get w to the 8th like that. So now this answer is currently looking like w squared. Oh, and w squared, remove the 2 w's from here, remove 2 of the w's from here, you have 6. So let me get rid of that w squared. So on top, we have the square root of w, or the cube root of w, times the square root of w divided by 5w to the 6th power. Now, we wouldn't be done here in my eyes because I don't like 2 different radicals here. I'd rather just have 1. But how do we write the same radical? Because I can't put these w's together if they're not the same index. This is a 2. Remember, this is a 2, and that's a 3. this is where I'd probably want to work in terms of the rational exponents form. This is w to the 1/3, and this is w to the 1/2, and they are multiplying. Not the 1/3 and 1/2, but the w's are multiplying. So if they're multiplying, you can add them together. That's w to the 1/3 plus 1/2 over 5w to the 6th power. Now 1/3 plus 1/2 is a common denominator. Multiply this by 2 over 2 and 3 over 3. This becomes w to the 2 over 2, 2/6 plus 3 over 3, 3/6 over 5w to the 6th, which equals w to the 5/6 over 5. What? That's a 5. That's not a w. Which is w to the 5/6, w to the 5/6 power over 5w to the 6th. Now, if you're thinking about subtracting these two, that's a possibility. What I would encourage you to do, though, is not, because, and I'm not done, I'm going to rewrite it in radical form, because that would make your denominator irrational again. That would make your denominator irrational, and there's no reason we want to go back and do that. But I can rewrite this thing as the 6th root of w to the 5th power, which, as you can tell, it can't be simplified anymore, and that's 5w to the 6th. So that's my preferred answer for this one. The denominator is rationalized, I should say. Denominator is rationalized, and we got things simplified kind of to the best of our ability. But it really had to do with fusing these into one radical, and that's done by doing common denominator stuff with fractions. So fraction usage is really good for variables, or when you're not evaluating what's inside of there, and more so working out how to work them together. Fraction exponents to me are the key. Number 62. I mean, these problems are going in the deep end, guys. They're not just doing quick versions of examples with the things. They're taking things and going beyond. They really are. Number 62, you have the 4th root of v to the 6th divided by the 7th root of v to the 5th. The bottom I can't do much with. I am going to have to rationalize the bottom, but I can't do much with it now. And these also aren't the same radical. So the question is, and this is something I don't know the answer to, the question is, should I go for the same radical first and put them together? Or should I try and simplify things where I can and then go from there? I'm going to just simplify first and see what to do with it afterward. I'm at odds with myself and what's going to happen. But on the top, remember, this is, keep in mind, this is v to the 6 over 4 power, which is v to the 3 over 2 power. Now, I'm going to rewrite that as the 2nd root or square root of v cubed. And by the way, I can still simplify what's inside there. I'm not even done, because square root of v cubed, 3 divided by 2, is 1 with a remainder of 1. So v times the square root of v over the 7th root of v to the 5th. Now, 2 reasons we're not done here. 1, they're not fused together as one radical. 2, I can't have an irrational denominator. Remember, 5 can't divide by 7, so we can't do anything there. But let's try and rationalize it. Let's try and, I'm going to copy and paste that down here. Let's try and rationalize that denominator here. We've seen this before. I need to turn v to the 5th into v to the 7th. So I got to take the 7th root of v squared, because 2 plus 5 is 7. So I'll get 7th root of v squared, 7th root of v squared. So on bottom, we'll now have v. It'll be the 7th root of v to the 7th power, which is v. Awesome. On top, we have a v, by the way, which means those can eventually cancel, but we're still dealing with now a square root of v times the 7th root of v squared. So as these ones, yes, indeed, do cancel out, they are actually gone. We're now down to the square root of v times the 7th root of v squared. Now I might want to rewrite that v. Square root of v is v to the 1/2 power. V to the 1/2 power times, this is v to the 2/7 power. We got to get a common denominator here. Multiply this by 7 over 7, you get 7 over 14. Multiply this by 2 over 2, you get 4 over 14. Oh, these add, by the way. And then this becomes v to the 11 over 14th power, which in radical form would be rewritten as the 14th root of v to the 11th power, and that would be my simplified result. Was it the fastest way to get there? I don't know. I can't guarantee that. You have to keep a lot of things in mind here. V couldn't ever equal 0, but because we're dealing with positive variables only, that's not something we really have to discuss. But that's what it is. That's an 11, by the way. That is not a 4. I don't know if I salvaged it enough. Let me erase it and change it. My middle finger needs a break here. from this pen, it gets a little messed up here. So I'm just slowly working on that. Okay, number 63 and 64, yowzas, right? They already have fractional exponents. Maybe the final answer would be written with them. I personally often prefer to have the, gosh, that does hurt. I'm gonna need a break, man. I personally do prefer in some ways the radicals when all said and done, because you have to remember you can't have fractional exponents in a denominator either, because that's like having an irrational denominator. So we might have to do something with that. All right, we have 18 w to the 1/3 v to the 5/4 over 27 times w to the 4/3 times v to the 1/2. Once again, we treat numbers with numbers, w's with w's, v's with v's. Don't forget that. 18 over 27 does reduce to 2/3. I'm going to start with that one straight up. That won't change no matter what I do here. So 2/3 is there. Now, with these ones, the 1/3 minus 4/3, right, we are subtracting. It's harder for me to say, oh, you remove 1/3 here and you're left with, that's harder for me to say. So let's just kind of work that out. W to the 1/3 minus 4/3, that becomes w to the negative 3/3, which is w to the negative first power. Now, w to the negative first power would be in the numerator. That means it's a w in the denominator. All right, so there's a w that sits down here. That's how that's going to work. Let's work with the v's. I didn't really give myself enough room to work with the v's. I wrote the w's on top just out of happenstance. Let's try to fit the v's right down below, maybe in a different color. Let's do v to the 5/4 minus v, or divided by, because they're divided, the exponents subtract, right? So minus 1/2. And that is, get a common denominator, that's 5/4 minus 2/4, like that, which is v to the 3/4 power. Now that's going to be in the numerator, right? It's a positive number, so we still have a v to the 3/4 like this. We're pretty much done. There's no irrational denominator there, which is nice. If you do want to keep it like this, I'm sure that's fine. Because it started off as fractions, maybe we keep it as fractions. What I'm going to also, I don't know if encourage, but I'm going to also write as another one that I like to see is the cube root like that. So that works out to me as well. 2 times the 4th root of v cubed over 3w. Looking pretty good there. Like I said, if the thing just leaves it as fractional exponents, you're good to go either way. All right, number 64, last one of this set. We have 7x to the negative 3rd, or negative 3/4, times y to the 5/2 times z to the negative 2/3 over 56 x to the negative 1/2 and y to the 1/4. Now, you've heard me before. I'm personally a fan of turning negatives positive by moving them in other slots. So maybe if I'm going to get a full rewrite here, move these x's in different spots and move that z down below. Let's just get a full rewrite of this stuff as it is. 7 over 56, I'm going to start with that right now, though. That reduces to 1/8. As long as there's a 1 on top, as long as there's anything else on top other than that 1, I don't even need to write that 1, but I'll write it this first time. So x to the negative 1/2 turns into x to the positive 1/2 on top. This isn't a required step. It's just something that I personally prefer to do. And I got y to the 5/2 here still. I haven't touched that one. X to the negative 3/4 is now x to the positive 3/4 on bottom. With that y to the 1/4, that hasn't changed. That's still there. And z to the 2/3 is now on bottom as well. That was the number, right? 2/3, yeah. But it's positive on the bottom, right? So now we know where things are established and where they're supposed to be. Maybe you don't make as many mistakes in your subtraction. Normally, this benefits me. It might not here. Normally, this benefits me more when it comes to whole numbers. That way I know to cancel this thing out. If this said squared and this said cubed, I know I could cancel out these 2's and be left with just 1 down here. Because it's fractions, maybe it's not as much benefit. But would you rather do 1/2 minus 3/4 or negative 3/4 minus negative 1/2? And then deal with where it goes. That gets a little tricky. So let's deal with those x's and y's with subtraction the same way that we did the previous sets. 1/2 minus 3/4 equals 2/4 minus 3/4, which is negative 1/4. That means it'll go in the denominator. For y's, 5/2 minus 1/4 is the same as 10/4 minus 1/4, which is 9/4. and that's a positive 9/4, so that'll stay in the numerator. Sorry for the small writing. 1 times anything is just that number. Keep in mind, there is no x on top anymore. It's going to go in the denominator, x to the negative 1/4. It's going to turn positive in the denominator. Y to the 9/4 is the only thing that remains on top in this problem. That's it. Now on bottom, I still have the 8. These ones turn into x to the 1/4 power, like that. And z to the 2/3 is down here as well. Remember, the y stuff already subtracted themselves out. Now, rationalizing denominator and stuff like that is still going to have to be had. First of all, when I work on the top here, this is where I'd want to talk about, 9/4, 9 divided by 4. 4 goes into 9 twice, so that's y squared. And then there's still a remainder of 1. Remember, the fourth root, or the fourth to the 1/4 power means the fourth root of. So this is 9 divided by 4 is 2 with a remainder of 1 out of that 4. On the bottom, I have 8 times the fourth root of x, that's no good for us, and times the cube root of z squared, that's also no good for us. So we got something simplified and worked out, but we're not fully done here. I still have the top as is, that's y squared times the fourth root of y. And on bottom, I still have this, obviously right here, but I need to work out rationalizing this denominator. 8 times fourth root of x times the cube root of z squared. There are 2 things I have to take care of. I have to take care of the x and the z. So we'll do them at the same time. There's no problem with that, but there will be a problem with respect to not having them have the same radical. We still have to deal with that as well. So for x, I still need to get, this is x to the first, I need to get to x to the fourth, so I still need 3 more x's there. This z just needs 1 more z inside there to become a z cubed. So I'll get the cube root of z to the first power. That'll get me a z cubed. So I need to multiply by that on top and bottom. Fourth root of x cubed. After this, I'm going to have to step out for 1 second. Times cube root of z. Like that. So there's a lot of work in this problem, guys. We're not even near done. All right, so x and y both exist inside a fourth root here. So when it comes to the top, I'll have y squared times the fourth root of x cubed times y. The cube root of z is its own radical for now. I can't really do anything with that as it stands. And on the bottom, x, well, there's 8. The fourth root of x times fourth root of x cubed is the fourth root of x to the fourth, which is x. That's what we wanted. Cube root of z squared times the cube root of z is the cube root of z cubed, which is z, which is what we wanted. So that's all worked out on bottom. The denominator's rationalized. This would almost be good as an answer, except I do want the same radical on top here. So what I need to deal with on the x cubed y and stuff and the z is to get a common denominator. So with these ones involved, this is just going to be some side work here. I'm going to be taking x cubed times y to the 1/4 times z to the 1/3, and I need to give them a common denominator here. I need to think about this one though, because these aren't the same variable. How do we do that before when they were different variables, or were they always the same? Maybe I can keep them separate, but I feel like I can do a little bit more. Okay, well here, how about this? Let's do this. Let's do the cube. Like basically, I want them to be 12s. I want them to be 12 like radicals, because that would be the least common multiple of 4 and 3. So if I turn this into the times 3, it was 3/12, like that. So it's not about adding these, so to speak. It's about getting them inside the same radical, right? So this would be z to the times 4 over 4 is 4/12. That means that both the x and the y will inherit an extra 3 basically. So this would become this is x cubed. Sorry, I'm writing these extra steps. X cubed times y cubed raised to the 1/12 times, because now these are actually going to be the same 1/12 here, times z to the 4th raised to the 1/12, right? That's the idea that's happening there. And both these get cubed. X cubed gets cubed, which becomes x to the 9th. Y gets cubed, which becomes y cubed, that's raised to the 1/12. And z gets to the 4th power, which is also raised to the 1/12. So all those are raised to the 1/12. which is another way of saying the 12th root of x to the 9th y cubed z to the 4th. It depends on whether you're writing it as this version or that version. Anyway, now they're the same radical. So my final answer I can write here, if I did this all correct and didn't make any mistakes, would be y squared on top times the 12th root of x to the 9th y cubed z to the 4th all over, was it 8xz? All over 8xz. The alternate, and that's one of those, would photomath answer it that way? I don't know, maybe. I'd hope so. The alternative answer is with the 1/12th power, which is y squared times x to the 9th y cubed z to the 4th to the 1/12th power, all divided by 8xz. The only reason I write that version is because they introduced it that way with fraction exponents, so I'll leave with fraction exponents. And because all those numbers are like that, I mean, that's a lot. Right, that's a lot. You can do it that way. You know, alternatively, look, we had this answer before. What was it? This one right here. This one's not bad. This one's not bad. At least the denominator's rationalized. At least you have something there. So if you want to leave it like this and leave them separate, you can do that. Again, if you had fractional exponents, then this would be x cubed y to the 1/4. You would want to put those together, times z to the 1/3 over 8xz. That's fine. So there's this or this, but in terms of getting one radical down, we'd want to have it just like this right here. This is my photomathy version of an answer. When I say photo, I'm not doing photomath. I'm just saying with my photomathy version of an answer, that's what I do. All right, let me pause. 1 sec. All right, missed me? Okay. All right, we finished that set. Okay, here we go. In exercises 65 to 70, perform the indicated operation, assume all variables are positive. So we're back to adding and subtracting, combining like terms, but if we gotta simplify some radicals inside, we'll do that. I think it's one of those ones, given they're only 2 terms, we're going to assume they can combine in some sort of way, right? There's only one problem so far where they haven't combined, and it was within that one set of like which things match, so that was kind of like an exception to the rule, even though I expected those ones to work out. So these ones straight up, they have like terms. 12 times cube root of y plus 9 times cube root of y. That is 21 times cube root of y. And that inside can't simplify anymore, so we'll leave it like that. What I really should get better at as well here is that, you know, this isn't 21 cubed. See, look, there's a difference, by the way. You know, 21 cubed times square root of y is not the same thing as 21 times the cube root of y. So I really got to get better at saying that, you know, this is the answer that we have right there. It's not 21 cubed. I really got to put that 3 inside the radical, you know, thing a little bit better for us as we do them. Number 66, we have 11 root 2z minus 5 root 2z. Hey, those terms are alike. You know what we can do? We can combine them. So 11 root 2z minus 5 root 2z equals 6 root 2z. That was 2z, or 2 easy. I guess that's not the same thing. Number 67. 3x to the 7 halves. I mean, who are they tricking here? Minus 5x to the 7 halves. They're both x to the 7 halves power. It's like 3x squared minus 5x squared, that kind of thing. It's not the same thing. But it's negative 2x to the 7 halves power, and we're going to leave it like that. Just like that. I don't think they're asking us to get into the... It says perform the operation. It's not saying simplify. Otherwise, I'd be turning into this whole x cubed root x, like that kind of thing. And we could, right? I don't think that's our end goal for this one. This is combining like terms where we can. If we need to simplify something with the variable expression to get them to combine, that's one thing. If they already combine, we're good. Like, let's take a look at number 68. On number 68, we have 7 times the cube root, there we go, of m to the 7th plus 3 times m to the 7/3. What we have to recognize is these are both the same thing, right? Now, would you rather write it like a radical or rational exponent? I'm more of the radical. I'm a radical guy. So I'm a rad dude, you know? So this is 7 times the cube root of m to the 7th. That hasn't changed. But this is 3 times the cube root of m to the 7th, right? That's what's actually happening here. They are equivalent. They are like terms, if you will. That 3 should get a little closer to that. The 7 should get a little closer too. 7 plus 3 is 10. You get 10 times the cube root of m to the 7th. If you'd instead prefer to write it like 10 times m to the 7/3 power, this is fine as well. Point is, they combine. They're trying to trick you with it, but they are equivalent. Number 69, we do have more to simplify before we kind of move forward here. And I'd like to simplify as much as possible. Whenever there's an option to simplify, simplify to the fullest extent of the law. And then, of course, combine like terms where you can. So here we have, okay, right here we have fourth root of 16 is 2. Now, w, the fourth root of w to the 10th is w to the 10 fourths power, which is w to the 5 halves power. Please do reduce that. So this isn't just 2 times the fourth root of w to the 10th or just divide, whatever. We are reducing that fraction as well. So w to the 5 halves is the square root of w to the 5th. I'm not done with what I want to do there. I'm just giving you part of the simplification that I want to work out before I keep moving forward. Now here is where we have to do the same thing. W to the 6 fourths is w to the 3 halves. Okay? W to the 3 halves means this is the square root of w cubed. Still not done. These still aren't even the same. 5 divided by 2, right, I didn't finish that. 5 divided by 2 is 2 with a remainder of 1. That means w squared can get pulled out, and a square root of w remains inside. This 2w is multiplying by the square root of w cubed. 3 divided by 2 is 1 with a remainder of 1. So there's that. That becomes 2w squared. So this is 2w squared root w plus 2w squared root w. They're the same thing. That doesn't mean that you just merge them as one, but you combine like terms. That becomes 4w squared root w. You're still adding the coefficients. Whether you treat the outside as the part that's the same, hey, add 2w squared to 2w squared, or whether you just say, hey, the w squared root w's are the same, add the 2's, whatever it is. Get a common factor. They're all the same thing. You get 4w squared root w. And I'm going to leave it in that form as opposed to any other form, but there we have. Number 70. Come on. Number 70, we have, they want you to work now, right? They go from the first questions, easy, easy, easy. Now they're going to these ones here where it's, make it work. P to the 1/2 times P to the 1/4 minus 4th root of 16p cubed. And, I want to once again remind you, look, I haven't seen these problems before. I'm not, that doesn't matter or not, but the point is, I'm working through these problems and just let's try things and see what happens. Now, I might see numbers a little more than you. Like I know that 1/2 plus 1/4 becomes whatever, and that's what I want to do with these right now. But try things and see what's going to work. So this is, yes, we have to add the 1/2 with the 1/4 with those ones to get those together. In this case here, I want to start working this out and simplifying it. 4th root of 16 is 2. And this stays as the 4th root of p cubed. I can't do anything there. 1/2 plus 1/4. 1/2 is 2/4. So 2/4 plus 1/4 is 3/4. So you get p to the 3/4 here. And this is minus 2 times. If you want to write this as p to the 3/4, you can. Let's just kind of get it started, right? Fractional exponent, p to the 3/4. This is 1 p to the 3/4 minus 2 p to the 3/4, which is negative 1 p to the 3/4. Let's just like that. So here's an answer. In radical form, it's this answer. Like that. Either or works. Make sure the negative is on the outside of it, though, not inside the radical. Just this is on the outside as well, right? You do this power first, and then you take the opposite of it. Okay. Numbers 71 and 72 find simplified expressions for the perimeter and area of the given figure. Now, there are two different given figures. So 71, we're going to do perimeter and area of that. Then 72, perimeter and area of that. I don't know which one is easier as far as which one would require less work, less hassle. So I'll just go in the order they stated. So here we have this guy here. It is a rectangle. Therefore, you have the same thing on both sides. So the perimeter is, we got to double each of these. We got to double x cubed, and we got to double 2x to the 2/3 power. Okay? So this becomes 2x cubed plus 4x to the 2/3 power. You'd be mistaken if you believe that every single thing you could do could clean itself up more. This is to the extent that I believe I can do perimeter. This is the cube root of x squared, and that can't pull out anymore, and this is x cubed there. That's the extent to which you can do the stuff for perimeter. That's it. The other problems were a little different because addition and subtraction were all that were had. This one also has area. Area is length times width. We have 2x to the 2/3 times x cubed. This is where a little more work is to be had as well. So for this guy, 2 doesn't matter, right? We're doing x's with x's. So x, we're going to add these two. We have 2/3 plus 3. 3 is 9/3. I'm going straight into it. So that'll be 2x to the 11/3. That's an answer. I don't know if they want to leave it like that or if there's more simplification to be had. If you consider other simplification options, it would be that whole cube root stuff. I think it's more that perform the indicated operation, get it that way. We got things simplified, I think, to a decent extent. I'll leave it like that for 71. 72, it's a triangle and a right triangle. So when we do area, it's going to be a 1/2 base times height thing. When we do perimeter, it's a different story, though. And it's easier than it looks. But remember, perimeter, we need that other length. We have to use Pythagorean theorem to get that other length. But as I stated, it's easier than it looks. You have to remember these are similar triangles every which way you see it. Both of these share an x to the 1/3 power. So it doesn't matter if this is x to the 1/3 power. It doesn't matter if this is a 10. It doesn't matter if it's a 1. This is a right triangle with 3 and 4 in its similarity of all this other stuff. So we got to find out what this number is by doing the square root of 3 squared plus 4 squared. Normally I use variables there, but 16 or 9 plus 16 and 25. It's a 3, 4, 5 special triangle, right? So this equals 5. It's a 3, 4, 5 triangle. So this is 5. That means this is 5x to the 1/3 power. I don't want to get deep in squaring x to the 1/3 powers and doing things like that and taking square roots. That's 5x to the 1/3 power. So when it comes to perimeter, your perimeter is 3x to the 1/3 power plus 4x to the 1/3 power plus 5x to the 1/3 power. And this is really where what the book does makes a lot more sense. I could have factored out x to the 1/3 from all of these and done 3 plus 4 plus 5, which is what we're going to do right now. That becomes 12x to the 1/3 power. Now I'm going to leave it like that. That is the perimeter of this right triangle. Its area is 1/2 base times height, and its base can be 4x to the 1/3. Its height can be 3x to the 1/3. So 1/2 base times height. Let's start with the numbers. Half of 4 is 2. 2 times 3 is 6, so we have that. And this is x to the 1/3 times x to the 1/3. That's x to the 1/3 squared, or x to the 1/3 plus 1/3, which is x to the 2/3 power. We're going to leave area just like that. I'm going to leave it alone. It's all good. It's all good. Okay, let's move forward. Number 73. We have 10 more questions. Modeling with mathematics. Optimum diameter D in millimeters of the pinhole in a pinhole camera can be modeled by that. I did pinhole cameras. I taught intro to engineering one year. So D equals 1.9 times, I've got some scientific notation going on here, 5.5 times 10 to the -4th L to the 1/2. That looks busy. I don't remember doing calculations like this. I just made the smallest pinhole possible. Where L is the length in millimeters of the camera box, find the optimum pinhole diameter for a camera box with a length of 10 centimeters. So we're going to do L is 10. Well, it says 10 centimeters. We need millimeters, right? How many? 10 millimeters is 1 centimeter. So is that 100 millimeters then that we're doing? Yeah? I'll make sure that's right. 10 centimeters is 100 millimeters because 1,000 millimeters. Yeah, I think so. Okay, anyway. So we now are going to be doing that substitution. So we're solving for D with this. We got 1.9 times. And this is a little busy looking. A lot of brackets. 1/2 power is also square root of. So I can do... And even this, well, let me clean this up a little bit. So this is 5.5 times, and listen, times like this, you don't need that. I can write it like this as well, right? 10 to the -4th power. And 100 is going in for L, and 100 is also 10 squared. So if I were to get a cleaned up version of this answer before I get the answer, we could kind of work it out like this. We don't have to go straight to calculator, right? This is all about practicing simplification rules. We can do that. This is 5.5 times, I guess now it's 10 to the -2nd power. 5.5 over 100, right? That's what we're doing. It's 5.5 over 10 squared, which is 5.5 over 100, which is, let me think about that. Hold on. 1.9 times square root of 5.5 over 100. So that would be 0.055. So 0.055. Let me try that in the calculator and see what kind of number we're dealing with. 0.055. Let's try 1.9. I got this. 1.9 times 0.055. And this answer is in millimeters. I'm getting 0.4455. Let's see. D is about 0.445, I guess 6 millimeters. I don't know how small you can get, like microscopically speaking, with regard to millimeters, even with like a computer to do something. Probably just about 0.45 millimeters. But that's what we're going to get for that one for the pinhole. There. Nice. Okay. Number 74. Modeling with mathematics. The surface area S in square centimeters of a mammal can be modeled by S equals km to the 2/3 power, 74, surface area. Okay, S equals, surface area is km to the 2/3 power, where m is the mass in grams of the mammal and k is a constant. Well, what constant? Oh, it's different per mammal. Humans, 11. Okay. The table shows the values of k for different mammals. Part A, find the surface area of a bat whose mass is 32 grams. So this is all substitution. As long as we're talking mass in grams, there we are. So 32 grams for part A. This is surface area of bat. And we're going to take its constant of 57.5 and multiply it by 32 to the 2/3 power. This isn't one I'm intending on doing any simplification stuff with. I just got to go and substitute. Plug and chug, right? 57.5 times 32 to the 2/3 power. Make sure you put 2/3 in parentheses. I know you can't see all this I'm typing out. I'm getting 579.56 surface area. I forget what this thing is. 579.56 square centimeters. That's a bat's thingy. But what about their size, right? Oh, it's based on their grams, duh. I was going to say, not all humans are the same, not all bats are the same. Part B, find the surface area of a rabbit whose mass is 3.4 kilograms. Now they do the conversion for you. 3.4 kilograms is 3,400 grams. So the surface area of a rabbit is going to equal its constant, which is 9.75 times, now we're going to say 3,400 grams, a little heavier than a bat, you'd say. I'm sure a human, even a little heavier than that, to the 2/3 power. So we're going to get something probably, well, it's got a different constant though, right? It covers, I don't know, it's denser in nature or something. I don't really know how this works. So 9.75 times 3,400 to the 2/3 power. Let's get it. We are getting it as 2204.57 square centimeters. 2204.57 square centimeters of that heavy of a rabbit. Part C, which mammal has the greatest mass per square centimeter of surface area, the bat or the rabbit, or a human whose mass is 59 kilograms? Well, let's start with the human. Now, 59 kilograms is 59,000 grams, so the surface area of le human is going to be based off the 59, let's see, 11 is their constant, 59 kilograms is 59,000 grams. We're going to go to the 2/3 power. Why didn't they just ask it straight up if they did this? But I don't know. Anyway, 11 times 59,000 raised to the 2/3 power gives us 16,670.96 square centimeters. Now, I'll use the rounded values. It should be enough as far as comparison's sake, even if it's not exact. I don't think they're going to be right next to each other. Now, who has the most surface area? Well, a human, but that's not what they're asking. Humans are going to be bigger than bats and rabbits, even like little baby ones. But the question is, which has the greatest mass per square centimeter of surface area? So, mass per square centimeter is going to be dividing this number by that number, and this number by that number, and this number by that number. So, for bat, I don't know if they call that density in a way, but I'll just say mass per whatever. I'll just say bat rate is going to be 32 over 579.56. Like that. We're going to check the rabbit as 3,400 divided by 2204.57. And we'll check the human, le human, as 59,000 divided by 16,000 something. 16,670.96. Now, which one is the greatest? Not the bat. Bat has less than 1. These have more than 1. Looks like it's still going to be the human when all said and done by quite a bit, actually, by quite a bit. When I do these ones, I'm going to be doing 32 over 579.56 for bat. I'm going to be doing, so that's way less than 1. I'm doing 3,400 divided by 2204.57 for the rabbit, which is a little more than 1. Human is going to be more than 3. 59,000 divided by 16,670.96. 3.53. So for the bat, I'm writing 0.06 grams per square centimeter. So I'm writing these out. Rabbit is 1.54 grams per square centimeter. And le human, lots of organs and stuff, 3.54 grams per square centimeter. So le human le wins. So human most. Human wins. Woohoo! We have the most grams per square centimeter. Look at us. Our surface area is not beat by the density of our somethings. All right. So that's it for number 74. Number 75. Making an argument. Let's see how our friend does this time around. Your friend claims it's not possible to simplify the expression 7 root 11 minus 9 root 44 because it doesn't contain like radicals. Is your friend correct? Explain your reasoning. Well, it doesn't contain like radicals, but let's make it contain like radicals. How about that, friend? Root 44 has a perfect square factor of 4 in it. If you factor that 4 out, you take the square root, you get 2. 2 times 19 is 18. You get 18 root 11, and now you can combine like terms. As per usual, the friend has been very, very wrong in chapters 2 and 3, and is starting to become wrong in chapter 4 as well. That can absolutely be simplified. We are at where we are at. Friend, wrong. You must simplify things if you're able to. And this is still to my... I'm not certain if this is certain. I don't think the friend was right once in chapter 2, or there was a streak where he started to be wrong, he, she, they. And I think they were right in section 3.1. And I don't know if they've been right since then afterward. I think there was one where I was making an argument with friend. Like, that was the problem. It says, your friend says this, you argue this, and then we were wrong, which was kind of a weird kind of way of saying it because I wouldn't have made the argument. Outside of that, friend has been wrong, and I'm waiting for the friend to get a streak of right. So, anyway, number 76 on problem solving. The apparent magnitude of a star is a number that indicates how faint the star is in relation to other stars. The expression here tells how many times fainter a star with apparent magnitude M1 is than a star with apparent magnitude M2. So there's a lot of this stuff here. There's a whole table and all that. Now, as far as this, I'm going to start by writing that out. I want to first just bring about the fact that, well, you can't cancel these things out through division like this. What you can do, if you'd like to, is rewrite it as 2.512 to the M1 minus M2 power. So we can work it out that way. Just make sure you're in parentheses when you do it in the calculator. We got the stars Vega, Altair, and Deneb with these magnitudes in these constellations. I don't know if the constellations matter, but they're the magnitudes. Part A, how many times fainter is Altair than Vega? So you got to compare, let's see, Altair is fainter. I think that's the M1. How much fainter M1 is than M2? So we got to do, so Altair to Vega is what we're doing here as far as faintness goes. We're going to be doing 2.512 to the 0.77 minus 0.03 power, basically. Or 2.512 to the 0.74 power. That's what we're going to look at. So I'll go to the calculator. I guess we don't need parentheses. 2.512 to the 0.74 power gives us 1.977. So it's 1.977. It's approximated, but times fainter as far as answering that question goes. About 2 times fainter, twice as faint. Part B, how many times fainter is Deneb than Altair? Deneb, Altair, we're going to be doing the same stuff. 2.512 to the 1.25 minus 0.77 power. This is where I make a mistake on subtraction here. Is 2.512 to the 48.48 power. I'm going to go with that. So do that one rise to the 0.48, and I'm getting 1.555999. It's about 1.56. Oh, let's see. 1.556 times fainter. Part C, how many times fainter is Deneb than Vega? Deneb to Vega. Heyo. So we're going to do 2.512 to the 1.25 minus 0.03 power. It's 0.03? Yes. Which is 2.512 to the 1.22 power. It's significantly fainter. Here we go. 2.512 raised to the 1.22 power, and I'm getting 3.07-ish. So about 3.076 times fainter. Now, I want to show you the calculator for a second here. And my curiosity will strike with what I believe to be true. I'm not thinking of the thing because I'm talking right now. But I want to show you the calculator for a second for this stuff here. Look at these numbers, 1.977, 1.556, and 3. In the calculator, I got those answers there. Boom, boom, boom. Okay. I believe that this times this should give me this because it was one and the other, if that makes sense. So I should be able to do because 0.74 plus 0.48 is 1.22. So if I did, I'm gonna do the rough numbers. This number times this number, it's gonna get close to 3.076, right? So that should be the same thing, and maybe that's what they wanted you to do. Just multiply those two, work off that idea of how many times fainter it is. Okay, then there's a constellation on bottom. I think they're just showing you a picture. I don't think we had to do anything with that. They're just giving you factual information. All right, number 77 on critical thinking. Probably want to copy that figure over. Find a radical expression for the perimeter of the triangle inscribed in the square shown. Simplify the expression. Well, give me a second. All right, well, what do we see here? They said it's a square. Square tells you several things: right angles and congruent sides. As far as right angles go, Pythagorean theorem can be of assistance to get these side lengths. As far as congruent sides go, 4 plus 4 is 8, and that's 8 as well. That means this has to be 8, and so does this, but 8 minus 2 is 6. Okay. We got to find the perimeter of this triangle, and we got to use Pythagorean theorem on this triangle here. I'm going to start with this one because I think it's the easiest to find the numbers in. This is a 3, 4, 5 triangle, 6, 8, 10. That length is 10. Now we got to use Pythagorean theorem on green and on purple, which seem to be similar. They are similar triangles. So if I find this one, I can double the length, and I believe I get that one. Or I can use Pythagorean theorem on those two. Actually, I don't know that's a right triangle, but these are right triangles themselves, so that works. Anyway, 2 squared plus 4 squared equals, I'll just call x squared. Oh, this should be green. 2 squared plus 4 squared equals x squared. That's 4. 4 plus 16 equals x squared. X squared equals 20. So x is the square root of 20. Square root of 20 is root 4 times root 5, or 2 root 5. So this is 2 root 5. If all is right with these things in right triangles, by side angle side similarity, this should be double, because double 2 is 4, double 4 is 8, so double 2 root 5 is 4 root 5. So that's how this should end up. So your final perimeter of this thing would simplify from doing 10 plus 2 root 5 plus 4 root 5, which is going to be 10 plus 6 root 5. Do they want us to round? Just says simplify the expression. So they expected some square root things like that. And that's what we got, 10 plus 6 root 5. Oh, I didn't bring down the little circle thingy. My bad. Highlighting that, but I'm going to move on to the next problem anyway. 5 more questions, I believe. Number 78. How do you see it? Without finding points, match the functions f of x equals square root of 64x squared and g of x equals cube root of 64x to the 6 with their graphs. Explain the reasoning. Well, if we take the square root of 64x squared, we will get 8 times the absolute value of x. So therefore, that should be b. Absolute value of x is a v-shaped graph. An absolute value occurs. Now we're talking about functions. We're not assuming variables are positive. In fact, we're looking at negative variables right there. Negative x's, negative x's. So that's where absolute value needs to kick in with the square root of a squared value. Whereas g of x must be a because, well, we'll find out. Cube root of 64x squared, x to the 6 equals, cube root of 64 is 4, and 6 divided by 3 is 2. You get 4x squared. That's a quadratic. That's a u shape there. We get a. My explanations in my equations, this is a v, this is a u. Probably not looking like that u, but there it is. All right, number 79. Rewriting a formula. You have filled 2 round balloons with water. One balloon contains twice as much water as the other balloon. Those are volume things. All right. Part A, solve the formula for the volume of a sphere, v equals 4/3 pi r cubed for r. So when they say solve, they're saying get r by itself. Make it say r equals. So 4/3 pi r cubed. Let's solve for r by dividing both sides by pi. So 4/3 r cubed equals v over pi. Let's multiply both sides by 3/4. And we get r cubed equals 3v over 4 pi. Let's take the cube root of r, and we get r equals the cube root of 3v over 4 pi. I don't know whether we're supposed to simplify that expression. Normally, it's one of these kinds of things where it would be more of a hassle to do so because it's more about substituting values to compute things. So I'm going to guess we're probably not simplifying it. I don't know if you're interested in looking at the simplified version, but I'm just going to leave it as is. So unless it says simplify, which I'm looking at, it does not. I'm going to go ahead and leave it. Part B. Substitute the expression for r from part A into the formula for the surface area of a sphere, s equals 4 pi r squared, simplified to show that s would equal this thing. Now notice how they have it. They have fractional values, so maybe we want to turn r's into a fractional as well when we do this. So r can also equal this to the 1/3 power. That's just another rewrite. So now surface area equals 4 pi r squared, or it equals, scroll up a little bit, or it equals 4 pi times this squared. The first thing I'm going to do is make that the 2/3 power. So s equals 4 pi times 3v over 4 pi to the 2/3 power. Now, what do we want it to match? Okay, notice how they have no fraction in the end. That probably means they did a rationalizing the denominator thing as a whole. So what I want to start by doing is splitting that part up into their own separate things. So like 3v to the 2/3 over 4 pi to the 2/3. Our goal now is to rationalize this denominator. So I would love to multiply top and bottom here by 4 pi to the 1/3 power, because that'll give me a whole 4 pi on bottom. 4 pi to the 1/3 power, like that. Now on bottom, so I still have this 4 pi on top. This is times 3v to the 2/3 times 4 pi to the 1/3. And remember, I'm trying to match what they have, whatever it is. Now I have 4 pi on the bottom because that's 4 pi to the 3/3. 4 pi over 4 pi is 1. They kind of just have it on top now. So s equals that. And they have the same thing written. They just have the 4 pi to the 1/3 written first. So s equals 4 pi to the 1/3 power times 3v to the 2/3 power. And that seems to match up all the same. Okay, part C. Compare the surface areas of the 2 water balloons using the formula in part B. So we'll call we'll call the volume of the, let's see, they say one balloon contains twice as much water as the other balloon. So when I have like the volume of object 1, I'll call that x. The volume of object 2, I'll just call it 2x, like that. So comparing them as far as surface area goes, or should I say 1v and 2v? Just v and 2v. If this has volume v, this is volume 2v, like that. So one will be double the amount. So let's go. Oh, let's see. What would the answer be? It would be the cube root of 4, I think. 2 to the 2/3. I don't know. Anyway, so we got s equals, s sub 1 equals this, right? 4 pi to the 1/3 times 3v to the 2/3. Now s sub 2 is going to be 4 pi to the 1/3 times 3 times 2v to the 2/3. 3 times 2v is 6v. So when it says compare them, I think we're just like dividing the bigger one by the smaller one, I think we eventually want to do. So let's write that. S2 over S1. I don't know for sure, but I think that makes most sense for things that'll cancel, stuff like that. 4 pi to the 1/3 times, now 3 times 2 is 6. So we got 6v to the 2/3 over 4 pi to the 1/3 times 3v to the 2/3. Now, when it comes to this, we have 4 pi to the 1/3 over 4 pi to the 1/3 is 0. These can be rewritten within the same, like, parentheses here. 6v over 3v raised to the 2/3 power, like that. So 6 v over v cancels, and 6 over 3 is 2. So s sub 2 over s sub 1 equals 2 to the 2/3 power. This can be an answer. It's kind of a weird one. I'd prefer to do the cube root of 2 squared, which is the cube root of 4. That's what I was saying. So the volume of the, or the surface area of the bigger one is the cube root of 4 times larger, I think that's the number I said, than the surface area of the smaller one. The surface area of the bigger water balloon is cube root of 4 times larger than the surface area of the smaller water balloon. Let me write the cube root of 4. Cube root of 4, like that. All right, there we go. Okay, number 80, thought-provoking. Determine whether the expressions x squared to the 1/6 power and x to the 1/6 squared are equivalent for all values of x. No, this is actually something that I had brought up before. They're not really saying explain. Obviously, I'll explain it to you guys. Here's the thing. Obviously, when you have these separately, sorry, not when you have them separately, if they ask you to simplify something, you're thinking, oh, yeah, just do 2 times 1/6 and you get x to the 1/3, and here you get x to the 1/3. But they're not the same, though. The reason is because when you have a negative value for x, squaring a negative value turns it positive here. A positive number raised to the 1/6 power leaves you with this. This is fine. But this does not equal this all the time. This only equals this for x's that are greater than or equal to 0. Because if you have a negative value that goes in for x here, a negative value, to the 1/6 power is the 6th root of. If you take the 6th root of a negative number, you get a non-real answer. Even if you work with the imaginary value, when you square it, it turns negative. Squaring an imaginary number turns it negative. So that won't get you what you're looking, well, I take it back. I guess that's the negative number here. But we're not treating it for real values. It says for all values of x there. So this is for x is greater than or equal to 0. This is for all x values, for all real numbers. This is only for x's that are 0 or positive for that one. That's where you have to be careful when it comes to order of operations. That's why I said the book would probably generally like to do this one before that one or something like that when they're doing certain problems. You just got to be careful for those ones. So the expressions would be different then. Okay, number 81. Drawing conclusions. Substitute different combinations of odd and even positive integers for m and n in the expression the nth root of x to the m. When you cannot assume x is positive, explain when absolute value is needed in simplifying the expression. All right, well, I guess we have to test it here. So the nth root of x to the m, let's try a couple different things. Remember, we're not assuming x is positive. So the square root of x squared was the absolute value of x. The fourth root of x to the fourth was the absolute value of x. Sixth root of x to the sixth was absolute value of x. So when they're equal in this, you take absolute value as long as they're both even. When they're equal and even, you take absolute value. That is a for sure. So we're going to conclude that as part of it. So when m equals n and are even, use absolute value. How about when they are equal and odd? When m, so let's see. We got, sorry, I guess I don't need to write that anymore. We can do, well, we can just write it right here. We don't do the first root, but the cube root of x cubed is just x. Fifth root of x to the fifth is just x. Seventh root of x to the seventh is just x. Anyway, I'm not going to do more of those. I'm not going to do multiple of those each time like that anymore. But when m equals n and are odd, I mean, we've done a bunch of these already, so that's not a surprise. And are odd, don't use absolute value. I mean, it's not that, maybe you can, maybe you can't. You don't. Otherwise, you're saying something incorrect there. Do not. Now, what are some other instances that we saw? We did see doing division of something where, let's try this. Let's try a bigger number divided by a smaller number, if that makes sense. Like x to the sixth and then the square root of that. They're both even. But here you get x cubed. Now, if x was a negative number, and then you did this, now we have x cubed. Cubing a negative number would turn it negative, but this should be positive here. So this needs to have the absolute value. We got to take the absolute value of x and then cube it. Assume that for all even numbers. So now we're making a bigger conclusion. When m is and n are even, use absolute value. I think that sounds like it's a bigger thing. Now, the other thing is that m needs to be bigger than m. Otherwise, we're still inside of the radical in some way. We might still have to use absolute values for those anyway. Hold on. Let's establish that. Let's do the sixth root. Maybe it is good that I'm trying these. The sixth root of x squared. And remember, that's x to the 2 over 6, which is x to the 1/3, which is the cube root of x. So in the cube root of x case, if x is negative, you can take its cube root. Here, same thing. Yeah, when m and n are even, doesn't matter if they're equal, less than, or greater than. Here's our final conclusion with that. Use absolute value. When they're both odd, it seems like we don't use absolute value. Let's say they're opposite. One's odd, one's even. Which one's the m, which one's the n? Okay. Let's do the cube root of x to the 6, and we get x squared, right? We don't need to use absolute value here. We can, whether you put this or not is up to you. That becomes a redundancy by putting it. That's when it's bigger. That's when this one's odd and that one's or even and odd. Let's try the cube root of x to the 6th. We can't take a negative root with that thing, so I don't know how much we're playing simplification with that. I don't think we need it there as well. It just is what it is. It would only work if it's positive. So that would be, the square root of x is x to the 1/2 power. So that's the square root of x. It would only work if positive or 0 anyway, so I think we're good there. And I don't think it changes if we have some sort of division. What we haven't tried yet is doing ones that are non-fractional, or that are fractional but you pull something out. So let's try something like, hold on. When m and n are different, I'll just say don't use it. There may be a level of redundancy, but I'll say it is redundant to use. When I say different, I mean different from odd and even. There's that. So don't use absolute value here. They don't need to be equal, by the way, when m and n are odd. I'm really just working on them. I'm working up my own version of this. So when m and n are odd, don't use absolute value. When they're even, use absolute value. When they're different, it's redundant to use absolute value. So you might as well just not. Does that work for all of them, though? Let's work for one more kind. Let's do this one. I mean, one more set. What if we have this? 7, 3 goes into 7 2 times, and there's a remainder of 1 inside there. Now, let's say we had a negative, right? Let's say we had a negative. Negative, results in negative, and this is positive times a negative. That's still negative. So that's all good. I think this takes care of it. I don't think it matters what you do beyond that. So those are the 3 things. When they're odd, you don't. When they're even, you do. And when they are different, you shouldn't, because of the redundancy. It doesn't hurt to use it, but just using it is just the way that works out. I think that's how I want to say it. I don't know if that's perfect, but that's how I'm going about it. Okay, so last question here is number 82 on rewriting a formula. It says rewrite the formula in exercise 74, so I got to find it, so that one side is m over s. Use this formula to justify your answer in part C. What was 74? Was that the density? Was that the human thing? Okay, so that was this one. So number 74, they said rewrite the formula so that one side is m over s. So s equals k m to the 2/3 power. Whoops. I lost my screen. One side is m over s. That means that you need... I'm not sure I get it. Can I do this? Can I do times? Basically, I'm doing rationalization without it involving the denominator. I need to find a way to turn one of these things into m, basically. So I'm going to turn this into s equals k times m to the 2/3 times m to the 1/3 is m, and this is over m to the 1/3 power. I want to end up bringing this m down here. I'm going to divide both sides by m, and now it says s over m equals k over m to the 1/3, which is also cube root of m. I don't know if I'm supposed to rationalize that or not, but that's just an appearance of it. Just working off that, we would get... oh, did they say s over m, or did they say m over s? Oh, they said m over s. Okay, just flip that. So m over s equals cube root of m over k. All right, so here's our rewrite of that. At least it's rationalized now, right? We have a rationalized version of it. Now they said use this formula to justify your answer in part C. So in part C, what I would do is... Well, m over s is the... Oh, okay, this is the mass per surface area. So let's use this version of this thing. Let's use the cube root of our mass over our constant and figure those ones out. So the masses that we have... 74. The masses that we have are 32, 3,400, and 59,000, and the constants we'll use in the table from the other one. Actually, we can just look at that problem there. So 74, we have all the numbers there, right? The humans is 59. Okay, yeah, we can just use those. So on this last bit, we can go to... Did I lose a page? Oh, here it is. Oh, I wrote 74. That's why it's weird. This is 82. I'm sorry. All right, this is number 82. Okay, so let's go and use this formula here, this m over s. So we're going to try for the bat, we're going to try cube root of its mass of 32 over its constant, which is 57.5. We should get, what was it? It was like 0.05 or something. No. The density. Oh, I don't have that number anymore. I think when we see it, we'll know. So let me try this. Cube root of 32. Cube root of 32, and then divided by 57.5. Yeah, it was that number, the 0.05 number. So I got 0.06 is the way that I put it. I put 0.06. This was grams per square centimeter, I believe. So check, that one works out. And then let's do the wabbit. The rabbit is the cube root of 3,400. That was the mass in grams over 9.75. So let's try that one. Cube root of 3,400. I guess you're just going to have to trust what I'm typing. I mean, it's up to you. Divided by 9.75. And I'm getting 1.54. I don't remember if that was a number. Actually, I do remember. I said it was a little bit more than 1. Somewhere between 1 and 2. So I'm just going to trust that one. And then the human, I mean, listen, the formula's working. They're just saying confirm that it works. And I think if we're getting numbers, we'll confirm it. That was 59,000 grams. So 59,000 grams, cube root of 59,000 divided by 11. Divided by 11, I'm getting 3.54 about. Oh, cube root of 50, that's not a 5. 59,000 divided by 11, which is about 3.54 grams per square centimeter. And I think that was that one as well. Somewhere between 3 and 4, I believe it was. Okay, guys, that was a lot of work, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Coming up in section 4.3, I believe, is graphing radicals, and I'm going to go into form of tableless graphing as often as I can. I believe the books can use tables, so figure out what you want to do with that. Just give me the heads up. Thank you. Take care. I will see you in the next one.